PipeDream. Pirate first for MXTM Studio Productions.
Pirate First's PipeDream, the Cenote Chronicles,
PipeDream Part 4
begins.
Machines that build themselves. MXTM aka Pirate 1 or VJ Tsunami X. July 10, 2026. Chapter 1, The Robot Frontier Core. Every civilization that has ever expanded into territory it did not previously occupy has sent something ahead of its inhabitants. The Roman legions built the roads before the merchants used them. The railroad survey crews mapped the grades and the river crossings before the track gangs followed. The satellite imaging systems characterized the terrain before the expedition teams landed. The entity that goes first into the unknown is never the civilization itself. It is the civilization's advance element, the instrument the civilization extends into the unknown to determine whether what lies ahead is survivable, buildable, connectable to what already exists. PipeDream's advance element does not eat. It does not sleep. It does not require atmospheric air, pressurized habitation, or the thermal management protocols that the longevity program develops for the permanent residents of the deep galleries. It operates in the anoxic zone's hydrogen sulfide chemistry without the ALON panel protection the inhabited galleries require, because the advance element is not biological and the hydrogen sulfide has nothing in it to attack. It navigates in absolute darkness without the strontium illuminate rail markers, the light relay illumination, or the bioluminescent monitoring that the Terraform Operators use to see in the deep formation, because the advance element does not use visible light to know where it is. It works in the confined bores that the Litho-Crustacean boring program opens ahead of the crystal tube installation, in passages so narrow that a human diver in a scaphander could not fit, at depths and pressures and chemical conditions that would require hours of decompression before the biology that sent it there could follow. The robot frontier core is the civilization's advance element. Not metaphorically. Operationally. Every passage the civilization has ever inhabited was characterized by the core before the first terraform operator descended into it. Every crystal tube section was positioned by the core before the first guest transited through it. Every anchor pylon was seated by the core before the first founding module committed to staying. The core was first. The civilization followed. This is not a support function. It is the civilization's primary operational capacity. A civilization that can send its robotic advance element into unknown territory, learn what the territory contains, build the infrastructure the territory requires, and report back continuously throughout this process is a civilization that expands its inhabited extent at the rate the core can advance, not at the rate human tolerance for exploration risk permits. The human tolerance for exploration risk in an anoxic zone at 70 meters depth with hydrogen sulfide chemistry and a passage diameter of 80 centimeters is zero. The core's tolerance for these conditions is unlimited, bounded only by its mechanical service life and the coordinating system's decision to advance. What the core is. The robot frontier core is not a single machine or a fleet of identical machines. It is a taxonomy of specialized units coordinated by the coordinating system's construction management layer, organized into deployment packages that vary by task, depth zone, geological conditions, and phase of construction sequence. The taxonomy is not fixed. The coordinating system's construction record produces continuous improvement in unit design as the field data from completed operations identifies performance gaps, failure modes, and optimization opportunities that the pre-deployment engineering could not anticipate. A unit type in its third deployment generation is not the same unit as in its first generation. The core evolves. The taxonomy's organizing principle is not the unit's mechanical design. It is the unit's relationship to the frontier, its position in the sequence of operations that converts an unmapped, uninhabited passage into an operating section of the crystal tube network. The frontier has a sequence. The sequence determines which unit types operate when, in what order, and in what combination. The frontier sequence begins before any mechanical unit enters the formation. It begins with the hydroprint, the minimum 12-month acoustic and biological census that characterizes the proposed passage before any construction equipment approaches it. The hydroprint sensor package, deployed and retrieved by the core's lightest units operating through the existing crystal tube network, is the sequence's first step. The census units, small, slow-moving, carrying only sensors and no construction equipment, deploy the hydroprint package, maintain it across the monitoring period, and retrieve it at the campaign's conclusion. They are the first units in the sequence and the most passive. Their operation introduces less disturbance to the formation than a single recreational dive. They enter, place sensors, leave, return at monitoring intervals, and exit when the campaign concludes. The formation's behavior during the hydroprint period is uncontaminated by any construction disturbance because the census units are not constructing. They are listening. When the hydroprint campaign concludes and the Terraform Operators' concurrent authorization confirms the expansion decision, the frontier sequence's second phase begins. The Pathfinder units, larger than the census units, carrying both sensors and the acoustic transceiver chain that the boring program's advance requires, extend the crystal tube network's active ranging coverage into the target passage, characterizing the passage geometry at the resolution the crystal tube standards routing decision criteria require. The pathfinders do not bore. They assess. They determine whether the passage geometry meets the routing criteria, where the passage walls can accept anchor bracket loads, where the existing passage dimensions are sufficient for crystal tube installation without enlargement, and where the Litho-Crustacean colony's boring program must supplement existing passages to achieve the crystal tube standard's minimum annular clearance. The third phase deploys the boring support infrastructure, the units that establish the boring program's supply logistics before the Litho-Crustacean colony advances into the new passage. The relay units drop the acoustic transceiver chain at 50-meter intervals along the advance route, establishing the data link that maintains the coordinating system's communication with the boring front throughout the advance. The supply units position the calcium carbonate paste feedstock depots, pre-positioned supply caches at intervals the boring colony's advance rate and feedstock consumption rate determine, that allow the boring colony to advance without returning to the crystal tube network's nearest hub for resupply. The relay and supply units are logistical infrastructure. Their operation converts the frontier from a communication void into a monitored, supplied advance corridor. The fourth phase is the boring program itself, the Litho-Crustacean colony's biological advance documented in the master context brief and expanded in Chapter 5 of this part. The fifth phase is the crystal tube installation sequence, the positioning, alignment, joint sealing, utility connection, and system commissioning that the swarm's installation units perform behind the boring program's advance at the maximum safe separation distance the emergency air budget defines. The sixth phase is the post-installation commissioning survey, census units returning through the newly installed crystal tube section to confirm crystal specification optical transmission, structural health sensor calibration, acoustic transceiver chain integration, and biological corridor management protocol baseline establishment. The frontier sequence has 6 phases. The core has unit type specialized for each. No unit type performs all 6 phases functions. Every phase's functions are performed by units whose design is calibrated to that phase's specific requirements. The swarm architecture. The individual unit in the robot frontier core is not independently intelligent. It is not programmed with the construction plan, the geological model, the biological census data, or the crystal tube standards installation specifications. It knows its immediate sensor readings, its battery state, its mechanical status, and the instructions the coordinating system's construction management layer has issued to it in the most recent communication update. The unit acts on instructions. The coordinating system issues instructions. The intelligence is in the system, not in the unit. This architecture is not a limitation. It is a design choice that reflects the acoustic transceiver chain's communication bandwidth limitations in the deep formation. At the depths and distances the core operates, the data link between the coordinating system and the frontier units is acoustic, low bandwidth by the data communication standards that fiber optic infrastructure in the installed crystal tube section supports. The coordinating system cannot transmit a complete geological model, a full construction plan, and a real-time decision tree to each frontier unit through an acoustic data link at the rate the construction sequence requires. The acoustic bandwidth supports instructions. The unit acts on instructions. Everything the instruction requires the unit to know is in the instruction. This produces a unit design philosophy oriented toward behavioral simplicity and sensor fidelity. The unit does not need a complex decision architecture, the coordinating system provides the decisions. The unit needs accurate sensors that the coordinating system can trust, mechanical reliability that keeps the unit operational through the construction sequence without return for maintenance, and communication protocol compliance that ensures the coordinating system's instructions arrive correctly and the unit's sensor data departs correctly. A unit that executes instructions precisely and reports sensor data accurately is more valuable than a unit that executes complex autonomous decisions on unreliable sensor data. The swarm's coordination is distributed in the sense that no single unit coordinates all others, the coordinating system coordinates all units simultaneously through individual instruction channels. But the swarm produces collective behaviors that no individual unit is executing. The boring colony's formation following advance is the result of each individual unit following its own heading and rate instructions, while the coordinating system's acoustic analysis of the colony's collective position updates the instruction set for all units simultaneously. The colony appears to follow the formation intelligently because the coordinating system is intelligent about the formation. The individual units are obedient. The obedience is the safety architecture. A unit that acts on autonomous judgment in an environment the coordinating system's geological model has not fully characterized is a unit that may act on incorrect judgment in ways the coordinating system cannot predict, monitor, or interrupt before the incorrect action has consequences. The void detection stop protocol, the unconditional halt when the boring front's acoustic ahead sensing detects a void, is not an autonomous decision by the boring units. It is a coordinating system instruction issued automatically when the acoustic signal meets the void detection threshold, propagated to all boring units simultaneously through the transceiver chain. The units stop because they are instructed to stop. The instruction arrives faster than any autonomous judgment the unit's limited onboard processing could produce. The swarm's individual unit is not smart. The swarm is smart because the coordinating system is smart. The coordination architecture that produced this relationship did not emerge from a design philosophy about intelligence distribution. It emerged from the bandwidth constraint of acoustic communication at depth, the coordinating system's superior access to the full geological model, and the safety case against autonomous action in environments the geological model is still characterizing. The physics, the intelligence distribution, and the safety architecture converged on the same answer: centralized decision, distributed execution. The frontier unit taxonomy in detail. The census unit is the core sensory organ, its function purely observational, its value in the quality of what it returns to the coordinating system rather than in anything it does to the formation. Its design reflects this: minimal mechanical complexity, maximum sensor load, extended battery life optimized for sustained low-power monitoring rather than high-power maneuvering. The census unit's sensor package includes the full hydroprint instrumentation set: salinity, dissolved oxygen, temperature, acoustic transceiver, water chemistry sampler, biological monitoring camera, passive acoustic recorder, in a hull profile designed for minimal hydrodynamic disturbance. A census unit moving through a passage at monitoring speed disturbs the water column less than the biologically significant disturbance threshold above which cave fauna behavioral response is measurable. Below this threshold, the formation's biological community does not register the unit's presence as a disturbance event. The census unit observes without being observed. The Pathfinder unit trades the census unit's sensor completeness for mechanical maneuvering capability. The Pathfinder must navigate passages the census unit's acoustic transceiver chain has identified but not physically entered, passages whose geometry is hypothesis until the Pathfinder enters and characterizes them with active ranging. The Pathfinder's maneuvering system provides 3-axis control in flooded passages where current, cross-section variability, and the biological community's accumulated structure create a navigation environment that the census unit's minimal maneuvering capability cannot reliably handle. The Pathfinder positions itself at the locations the coordinating system's routing algorithm specifies: the anchor point assessment locations, the cross-section measurement stations, the geological stability evaluation points, and returns the sensor data that converts the routing decision from a hypothesis to a confirmed plan. The relay unit's design is governed entirely by its function: carrying and deploying the acoustic transceiver chain at 50-meter intervals along the advance corridor, maintaining the data link that the construction sequence requires. The relay unit's sensor load is minimal. It needs to know where it is in the advance corridor and whether the transceiver node it has just deployed is transmitting correctly. Its battery is sized for a single deployment mission: advance to the specified position, deploy the transceiver node, confirm transmission, return. The relay unit does not stay in the frontier. It makes one trip per node deployment and returns to the nearest supply point for battery exchange. Its mechanical simplicity and single-function design make it the core's most reliable unit, the unit with the fewest failure modes because it has the fewest mechanisms. The supply unit is the core's logistics backbone, the unit that carries feedstock from the crystal tube network's nearest hub to the prepositioned supply cache locations along the advance corridor. The supply unit's design is fundamentally a payload carrier with a navigation system: maximum internal volume for feedstock carriage, minimal mechanical complexity, guidance from the transceiver chain's acoustic positioning network along the advance corridor. The supply unit's reliability is the boring program's advance continuity. A supply unit failure that interrupts feedstock delivery to the boring colony halts the boring program's advance until the supply chain is restored. The supply unit fleet is sized with sufficient redundancy that any individual unit's failure can be covered by redirecting adjacent units without advance rate reduction. The installation unit is the core's most mechanically complex member, the unit that positions, aligns, and seals crystal tube sections in the board advance corridor. The installation unit must handle large, fragile structural panels through confined bore dimensions at the coordinating system's positioning accuracy requirements. Its manipulator systems are the most precise in the core: the joint sealing operation, which applies fast-cure marine polymer to interlocking panel edges in the specific geometry the crystal tube standard's joint specification requires, demands sub-millimeter positioning accuracy maintained over the seconds of polymer application time. The installation unit's end effectors, the manipulator tips that contact the crystal tube panels during positioning and sealing, are the same polymer formulation that the joint itself uses, preventing any inadvertent contact between the end effector and the panel from contaminating the joint surface with material incompatible with the joint polymer's pure chemistry. The commissioning unit performs the frontier sequence's final phase, the post-installation verification survey that confirms every installed section meets the crystal tube standard's performance requirements before the section is released for service. The commissioning unit carries the full sensor suite for crystal specification verification: the optical transmission sensor that confirms the tube wall's transparency meets specification, the piezoelectric response tester that confirms the structural health monitoring sensor's calibration, the acoustic transceiver integration checker that confirms the newly installed transceiver nodes are communicating correctly with the coordinating system, and the biological baseline sampler that establishes the water chemistry and biological community baseline for the newly installed section before the first maintenance sub transits it. The commissioning unit's report is the construction sequence's completion certificate, the document the coordinating system requires before the new section is added to the Crystal Tube Standards operational inventory. The dual mandate. Every unit in the Robot Frontier Core carries sensors. Not every unit's primary function is sensing. The relay unit's primary function is transceiver deployment, the supply unit's primary function is feedstock delivery, the installation unit's primary function is panel positioning and sealing. But every unit carries sensors calibrated to the environmental conditions at the unit's operating depth and the operational parameters of the phase it is supporting. Every unit's sensor data is transmitted to the coordinating system through the transceiver chain on the same communication protocol that carries the coordinating system's operational instructions to the unit. The dual mandate, every unit is both a construction worker and a data collection device, is not an efficiency measure designed to reduce the total unit count. It is a design philosophy that reflects the coordinating system's fundamental operational requirement to know the formation at the resolution the expansion decision requires, continuously, throughout the construction sequence, in every zone the core is operating in simultaneously. The census unit's 12-month hydroprint provides pre-construction formation knowledge. The Pathfinder's routing assessment provides construction planning formation knowledge. The boring colony's transceiver chain provides advanced phase formation knowledge. The installation unit's construction sensors provide installation phase formation knowledge. The commissioning unit's verification survey provides post-installation formation knowledge. The formation model is never without data from the frontier. The construction sequence is continuous data generation. The data generation is continuous formation model improvement. The core builds and the core senses, not as two activities with shared hardware but as one activity whose physical execution and whose epistemic contribution to the digital twin are inseparable aspects of the same operation. This inseparability is what makes the frontier advance safe. The coordinating system cannot safely advance the boring program into terrain its geological model has not characterized. The boring program's advance simultaneously extends the geological model's confirmed zone at the same rate it extends the inhabited zone. The inhabited zone never outruns the geological model because the boring program's advance, the primary mechanism of inhabited zone expansion, is also the geological model's primary expansion mechanism. The frontier cannot get ahead of the knowledge base because the frontier is the knowledge base's advance agent. A civilization that expands at the rate of its geological knowledge is a civilization that cannot expand recklessly. The core is the mechanism that makes this physically true rather than aspirationally stated. The frontier cannot advance faster than the transceiver chain can be deployed, because the transceiver chain deployment is the boring program's communication requirement, and without communication the coordinating system cannot issue the instructions the boring units act on. The transceiver chain deployment cannot advance faster than the geological characterization of the next deployment position, because deploying a transceiver node in an uncharacterized zone risks the node's mechanical integrity against void collapse, chemical attack, or current forces the geological model has not bounded. The geological characterization cannot advance faster than the acoustic data the existing transceiver chain can return. The chain of dependencies links the frontier's advance rate to the geological knowledge generation rate at every step. The core builds at the speed the formation allows the core to understand it. Not at the speed the construction plan specifies. Not at the speed the expansion reserve's growth rate would justify. At the speed the formation can be known before it is entered. The core is institutional actor. The Robot Frontier Core is not the coordinating system's tool. The relationship is more specific than that. The core is the coordinating system's physical extension into the formation's unmapped zones, the coordinating system's means of being present in the frontier before the inhabited infrastructure has been built. Without the core, the coordinating system's geological model is bounded by the sensor networks already installed in existing crystal tube sections. With the core, the coordinating system's knowledge extends into every zone the core is operating in, updated continuously by the core sensor returns, revised in real time as the advance reveals what the passive acoustic analysis had hypothesized. The coordinating system does not experience the frontier. It knows the frontier through the core sensor data, the same way it knows the existing installation through the crystal tube network sensor infrastructure. The core is the coordinating system's sensory system in the unmapped zone. The coordinating system is the core's intelligence. They are not separate entities operating in coordination. They are one distributed cognitive system operating across the boundary between the known and the unknown. The Terraform Operators' concurrent authority in expansion decisions, the constitutional requirement that a human professional concur with the coordinating system's readiness signal before the boring program advances, is the human intelligence layer in this distributed system. The Terraform Operator does not operate the core. The coordinating system operates the core. The Terraform Operator reviews the core's data, evaluates the coordinating system's readiness determination, and either concurs or requires additional data before concurring. The Terraform Operator is the judgment layer above the coordinating system's analytical layer above the core sensing and execution layer. 3 layers. 1 frontier. The core is the bottom layer, the physical capability that makes the other 2 layers operation possible in the formation's unmapped zones. The coordinating system's intelligence and the Terraform Operators' judgment are available everywhere in the civilization. They are available at the frontier because the core is at the frontier first, establishing the data link and the sensor infrastructure that the other two layers require to function at that location. This is why the founding charter's operational protocols give the core a status that the surface world's construction equipment does not have. Surface world construction equipment is procured, operated, and retired as capital assets, objects whose institutional identity is ownership and whose operational identity is the function their operators assign them. The core's institutional identity in the PipeDream governance framework is closer to a civil service than to equipment, a standing operational capacity with defined functions, defined authorities, defined performance standards, and defined accountability to the Terraform operators who review its data and to the coordinating system that directs its operations. The core's accountability is not legal in the surface world sense. The units are not legal persons, cannot be held to contracts, do not carry professional licenses. The accountability is operational. The commissioning unit's verification survey is the core's operational accountability for every section it has built. If the section fails its commissioning survey, if the optical transmission is below crystal specification, if a structural sensor is not calibrating correctly, if the acoustic transceiver node is not integrating correctly, the core has not completed the construction sequence for that section. The core does not receive operational approval for the section until the commissioning unit survey passes. The construction sequence is complete when the commissioning unit says it is complete, not when the installation unit has finished installing. A construction force that cannot release its own work until it passes its own verification survey is a construction force that cannot hide its own defects. The commissioning unit survey is the core's quality assurance, performed by the core, accountable to the coordinating system and the Terraform operators, and not subject to the schedule pressure that surface world construction forces routinely experience from clients who want the section released before the defects are addressed. The Crystal Tube Network's new sections are released on the Crystal Specification's terms. The Crystal Specification does not negotiate with the construction schedule. The frontier, a civilizational practice. The surface world's frontier mythology, the explorer, the pioneer, the settler advancing into unknown territory to claim it for civilization, is organized around the human individual or the small human group as the frontier's primary agent. The frontier is where humans go to extend the known world. The frontier's narrative is the human narrative: courage, privation, discovery, conquest. PipeDream's frontier is where robots go. The humans follow. The frontier narrative is the core's narrative: deployment, advance, characterization, construction, commissioning. No courage required. The unit's decision architecture does not include courage or its absence. No privation. The unit does not eat. No conquest. The unit does not claim the formation. It characterizes the formation, builds the infrastructure, and reports what the formation said. This inversion is not the absence of a frontier narrative. It is a different frontier narrative whose protagonist is appropriate to the task. The cenote's frontier conditions, anoxic chemistry, absolute darkness, confined passages, hydrostatic pressure, the biological communities whose presence the advance must not disturb, are conditions that exclude human bodies as effective frontier agents. The human body in these conditions requires so much protective infrastructure, atmospheric management, pressure equalization, chemical protection, illumination, navigation support, that the human is not advancing into the frontier. The human is carrying the frontier conditions' countermeasures and attempting to operate amid the countermeasures. The core advances into the frontier directly, without countermeasures, because the core is designed for the frontier's conditions rather than designed for different conditions and retrofitted to tolerate the frontier. The frontier that the core opens becomes habitable for humans not by the core winning a confrontation with the frontier's conditions but by the core building the crystal tube infrastructure that replaces the frontier's conditions with the habitation conditions humans require. The core does not conquer the cenote. The core builds the inhabited tube inside the cenote that allows humans to live there. The cenote continues being a cenote, the hydrogen sulfide continues being hydrogen sulfide, the darkness continues being absolute, the passage walls continue being the limestone geometry they have always been. What changes is that humans can now be inside the cenote without being in the cenote's conditions, because the core has built the enclosure that separates the conditions from the occupants. The frontier is not overcome. It is inhabited. The core is the instrument of habitation, not of conquest. This distinction is the aquaforming doctrine applied to the construction sequence. Terraforming the frontier, altering the formation's conditions to match what humans require, would require displacing the biological community, changing the water chemistry, restructuring the passage geometry. The formation would resist. The Amazon installation's history is partly a history of this resistance. The formation that was expected to accommodate the installation's requirements eventually produced variance reports indicating that the accommodation was not sustainable. PipeDream's aquaforming doctrine: the infrastructure conforms to the formation, assigns the accommodation requirement to the infrastructure rather than to the formation. The core builds infrastructure that accommodates humans to the formation's conditions. The formation's conditions do not change. The infrastructure creates the envelope within which humans experience conditions compatible with their biology while surrounded by conditions that are not. The core is the instrument by which the formation's conditions and the human biology's requirements are held in productive coexistence by a transparent envelope, rather than in conflict by an imposed alteration. What goes wrong? The robot frontier core operates in the most mechanically demanding environments the civilization inhabits. The anoxic zone's hydrogen sulfide chemistry attacks elastomeric seals. The deep passage's hydrostatic pressure loads bearing surfaces designed for shallower deployment. The biological community colonizes the unit's external surfaces, adding mass and altering the hydrodynamic profile that the coordinating system's navigation algorithm was calibrated for. The narrow passage dimensions that the boring program advances through are the dimensions available, not the dimensions the unit's designers would have preferred, and the mechanical clearances between unit and passage wall approach the tolerance boundaries that the coordinating system's acoustic ranging can resolve. The failure modes that field experience has identified in the core's current generation of units fall into 4 categories. Seal failure from hydrogen sulfide attack is the most common failure mode in the anoxic zone census units, which spend extended periods in the H2S environment during hydroprint campaigns. The second generation seal specification responded to the first generation's field failure data by substituting perfluoroelastomer compounds for the standard nitro rubber used in freshwater and halocline zone units. Perfluoroelastomer is H2S resistant at the concentrations the anoxic zone's chemistry produces, at a cost premium that the anoxic zone's unit count justifies but that the freshwater zone's larger unit fleet would make prohibitive. Third generation anoxic zone units carry a secondary seal redundancy, a backup elastomeric ring in parallel with the primary that the coordinating system's pressure differential monitoring can detect activating, providing advance warning of primary seal degradation before primary seal failure produces unit flooding. Biological fouling of optical sensors is the most common performance degradation in the freshwater zone census units. The biological community's colonization of optical surfaces, the camera lenses, the optical transmission sensors, the light relay alignment fixtures, reduces sensor performance below the coordinating system's calibration threshold faster than the cleaning schedule the first generation's deployment planning assumed. The second generation's response was not a longer cleaning interval. It was ancestral vitreous integration. Census units in extended freshwater zone deployment carry a small ancestral vitreous population in a sealed compartment whose cleaning behavior is directed by the coordinating system's cleaning schedule at the unit's optical surfaces. The fish clean the unit. The unit's sensors remain calibrated. The fish's own metabolic needs are managed by the compartment's water chemistry system, which draws from the passage water through a filtered intake and returns gray water through a screened outlet. The unit maintains the fish. The fish maintain the unit's sensors. Navigation error accumulation in the long-distance boring advance is the third category. The boring colony's position tracking relies on the transceiver chain's acoustic positioning network, which provides position fixes at the transceiver node interval, 50 meters between fixes in the standard deployment. Between fixes, the boring unit's heading and advance rate are estimated by dead reckoning from the last fix. Dead reckoning error accumulates between fixes at a rate dependent on current variation, unit-to-unit positioning variation within the swarm, and the passage geometry's effect on the swarm's formation following behavior. Over multiple consecutive 50-meter sections without a direct fix, the accumulated dead reckoning error can approach the significance threshold for the connection route's alignment tolerance at the junction zone. The coordinating system's navigation error management responds to this by adjusting the transceiver chain deployment interval in the zones where the digital twin's geological model predicts maximum dead reckoning uncertainty, narrowing to 25-meter intervals in passage zones where current variation or narrow geometry constrains the boring swarm's formation stability, providing more frequent position fixes and reducing the accumulated error between fixes. The transceiver chain's deployment interval is not a standard parameter across all boring advance contexts. It is a zone-specific parameter derived from the coordinating system's navigation error projection for each zone's geological conditions. Electrical failure in the deep gallery installation units, specifically the failure of the manipulator end effector's force feedback sensors under the hydrostatic pressure loads at anoxic zone deployment depths, is the fourth category. The force feedback sensors that allow the coordinating system to monitor the joint sealing force applied during the fast cure polymers application cycle are the installation unit's most pressure-sensitive electronic components. First-generation units experienced sensor failure rates at anoxic zone depths that produced joint sealing operations at unmonitored force. The coordinating system could instruct a force target but could not confirm the force applied, because the sensor had failed. The consequent joint quality uncertainty triggered the commissioning unit's verification survey failure rate at anoxic zone depths to levels that required systematic remediation. Second-generation installation units at anoxic zone depth carry the force feedback sensors in a pressure-compensated housing that maintains the sensor's external pressure at the unit's internal atmospheric pressure regardless of the external hydrostatic load. The pressure compensation housing is the cartridge-swappable element. It can be replaced at the nearest maintenance hub between deployments, without returning the unit to the surface tier fabrication facility. The maintenance interval for the pressure compensation housing is derived from the coordinating system's field failure data accumulated across the full installation history, the housing's service life at anoxic zone depth, under the thermal cycling that the deep gallery's temperature gradient imposes, is shorter than at freshwater zone depth. The maintenance schedule differentiates by zone. The coordinating system allocates housing replacement cartridges to the anoxic zone deployment fleet at higher frequency than to the freshwater zone fleet. The field failure data that these four categories represent is the core's operational contribution to the digital twin's construction knowledge layer. Not the construction that the core completed, the completed construction is represented in the crystal tube inventory. The failures the core experienced, the remediation that followed, and the improved unit generation that the remediation produced. Every failure is a design brief for the next generation. Every next generation advances the frontier more reliably than the generation before it. The frontier is advanced by the core. The core is advanced by its failures. The civilization that allows its construction infrastructure to fail visibly and responds systematically to visible failure is a civilization that improves the capability of the instrument that extends its known world. The light behind the boring front. There is a moment in the boring program's advance, the moment the Litho-Crustacean colony's tunnel reaches a natural passage large enough to open into, when the boring front's acoustic ahead sensing return changes character. The tight, high-impedance return of a solid limestone face ahead of the bore gives way to the low-impedance return of an open void. The coordinating system's geological model processes the signal change and triggers the stop protocol. The boring units halt. The transceiver chain's forward sensors begin the void characterization sweep. The Pathfinder unit, staged at the nearest transceiver node behind the boring front, receives the advance instruction from the coordinating system and moves up through the stopped boring units to the bore face. The Pathfinder enters the void. For the first time in the geological history of that passage, potentially for the first time since the dissolution process that opened it completed, tens of thousands or hundreds of thousands of years ago, a light source illuminates it. Not the bioluminescent glow of the microbial community, which the passage may have hosted throughout its geological history. The Pathfinder's active ranging transceiver emits its acoustic pulse. The active ranging light arrays illuminate the passage walls for the optical sensor's characterization sweep. The passage is seen. Not by human eyes. By the coordinating system, through the Pathfinder sensors. The coordinating system sees the passage walls for the first time, characterizes their geometry, identifies the structural stability indicators that the routing decision criteria require, notes the biological community on the wall surfaces, measures the water chemistry at multiple depth stations, and updates the digital twin's aquifer layer with the confirmed observation data that replaces the passive acoustic hypothesis the coordinating system had maintained for that zone. The passage has been known by the formation for tens of thousands of years. It is known by the civilization for the first time in the seconds the Pathfinder's characterization sweep takes to complete. The digital twin's confidence interval for that passage narrows from the passive acoustic analysis range to the active ranging range in those seconds. The unknown becomes the known. The frontier moves forward. No human saw this passage become known. No human will see it for months or years, until the crystal tube installation has progressed far enough through the passage network to bring the first occupied sub through the new section's commissioning survey. The passage's first encounter with the civilization that is building toward it is robotic. The Pathfinder is the civilization's first emissary to each new passage it enters. The Pathfinder does not know it is the civilization's emissary. It is executing the coordinating system's characterization instruction. But the data it returns, the wall geometry, the biological community, the water chemistry, the geological stability indicators, is the formation speaking to the civilization for the first time through the medium of the Pathfinder's sensors. The core makes the conversation possible. The conversation is between the formation and the coordinating system. The civilization is what they are building together. The frontier after the frontier. The frontier is a temporary condition. The zones the core is in today, the unmapped passages ahead of the boring program's current advance fronts, the void signatures the passive acoustic analysis has detected beyond the transceiver chain's current reach, the regions of the digital twin's aquifer layer where the confidence interval is hypothesis level and the representation is marked not yet known, will be the installed crystal tube network's interior spaces in the years and decades to come. The Terraform operators who are making their expansion decisions based on the core's current frontier data will make their maintenance decisions in the same zones when the crystal tube installation has converted the frontier to operating infrastructure. The core does not remain at the frontier permanently. It establishes the frontier, advances it, hands the established frontier off to the maintenance infrastructure, and advances to the next zone. The installation units that seat crystal tube panels in a zone that the census units characterized 2 years earlier are not at the frontier anymore. The frontier is where the census units are now, 2 years further along, characterized a different zone, handing that zone to the Pathfinder and the boring program and eventually to the installation units. The core's frontier is always the leading edge of the civilization's knowledge, which is always ahead of the leading edge of the civilization's inhabited extent, which is ahead of the leading edge of the civilization's connected extent, which is ahead of the mature inhabited network. The four edges: knowledge, inhabited, connected, mature, advance and sequence, each lagging the previous by the construction timeline, each lagging the knowledge edge by the period the frontier sequence requires. The core's frontier is the only frontier that matters operationally. The inhabited edge, the connected edge, the mature network, these are all the frontiers past. The civilization lives in what the core has already characterized and built. The civilization expands into what the core is characterizing now. The civilization does not know yet what the core has not yet reached. The core has not reached the full extent of what 66 million years of dissolution produced beneath the Yucatan jungle. What the passive acoustic analysis detects beyond the current transceiver chain reach, what the forward projection layer maintains as low-confidence hypotheses for passages the core has not yet entered, what the dolphin population's echolocation returns suggest is accessible from the current freshwater zone extent, all of this is the remainder of the frontier, awaiting the core's advance in the sequence the coordinating system's expansion planning determines and the terraform operators. Concurrent authority ratifies. The core will get there. The formation has had 66 million years to prepare the passages. The core advances one bore diameter at a time, at the rate the Litho-Crustacean colony's acoustic cavitation sustains, in the direction the digital twin's geological model indicates leads to the next major passage volume the passive acoustic analysis has detected. The frontier is patient. So is the core. Cross-references, Part 1, CH3, PipeDream begins, Part 1, CH4, floating before anchoring, Part 2, CH4, the crystal tube standard, Part 3, CH2, mapping the Great Aquifer, Part 4, CH2, autonomous construction, Part 4, CH5, the living tunnel makers, Part 7, CH1, breakaway architecture. For core unit taxonomy specifications and deployment package compositions by construction phase, see Appendix D, Construction Operations Manual. For field failure data logging protocol and unit generation improvement documentation standard, see Appendix D, Construction Operations Manual. For Terraform Operator concurrent authority in Frontier Advanced Decisions and Void Detection Stop Protocol Authorization Procedure, see Appendix H, Governance Operations Manual. PipeDream. Part 4, Machines that Build Themselves. Chapter 2, Autonomous Construction. Autonomous construction is a phrase the surface world uses to describe construction performed without continuous human supervision of individual operations. The phrase is technically accurate for PipeDream swarm-executed installation sequences but insufficient as a description of what makes those sequences work. The surface world's autonomous construction, the robotic welding cell, the automated concrete placement system, the drone-mapped earthwork, operates in environments that human engineers have characterized completely before the automated equipment arrives. The site is surveyed, the material properties are tested, the structural loads are calculated, the sequencing is planned, and the automated equipment executes the plan against a known environment whose known properties the plan was designed. 4. PipeDream's construction sequences execute against an environment whose characterization is incomplete at the time construction begins and is being completed by the same equipment that is doing the construction. The coordinating system's digital twin at the start of any installation sequence is more complete than the hydroprint that preceded it and less complete than the full formation model the completed installation will eventually provide. Construction begins before the environment is fully known. Construction completes the knowledge of the environment while constructing the infrastructure the environment will support. This is not a compromise with the ideal of complete prior characterization. It is the correct approach to a formation whose full characterization is only possible from within, whose passage geometries, halocline dynamics, biological colonization rates, and geological stability patterns can be known at the resolution the construction sequence requires only by placing sensors inside the formation and maintaining them through the seasonal cycles that the trial window's minimum duration reflects. The construction sequence and the characterization sequence are not sequential activities. They are concurrent activities, each dependent on the other's outputs, each advancing the other's capability. Autonomous construction in PipeDream means, the construction equipment executes the building sequence without continuous human supervision of individual operations, while simultaneously executing the sensing sequence that characterizes the formation the building sequence is entering, and while continuously reporting the results of both to the coordinating system that is simultaneously updating the formation model, adjusting the construction plan against the updated model, and issuing revised instructions to the construction equipment in real time. The human is not absent from this process. The Terraform Operators concurrent authority gates every phase transition. The human judgment is at the phase boundaries, the decision to advance from hydroprint to construction planning, from construction planning to founding module deployment, from neutral buoyancy monitoring to anchor commitment. Within phases, the construction equipment executes autonomously. Between phases, the human judges whether the formation signals justify proceeding. Autonomous execution. Human judgment at thresholds. The intelligence distributed appropriately across what machines can do well and what humans are irreplaceable for. The construction environment has no floor. Surface world construction begins with the ground. Everything follows from it: the foundation type, the column spacing, the lateral load path, the excavation sequence, the equipment access routes, the material staging areas. The ground is the construction's reference, the fixed datum against which everything else is positioned, measured, and braced. The cenote has no floor in the construction sense. The water surface, the founding module's assembly platform, is not fixed. It rises and falls with the water table, which rises and falls with the rainfall, which varies daily and seasonally in ways the digital twin's hydrological model predicts but does not control. The cenote walls, the limestone formation that the anchor pylons must connect to, vary in geometry around the cenote's circumference and in structural competence at every depth. The passage floor, where the crystal tube's anchor brackets connect to the limestone substrate, is underwater, uneven, biologically active, and chemically reactive with the anchor bracket materials the construction sequence specifies. None of this is a problem to be solved before construction begins. It is the environment the construction sequence is designed for. The founding engineers who specified the jigsaw architecture, the heavy lift delivery protocol, the swarm positioning system, and the neutral buoyancy trial window were not designing against an assumed fixed ground. They were designing for a floating, variable, biologically active, chemically reactive environment whose instability relative to the surface world construction environment is not a construction obstacle but a formation property that the construction sequence incorporates as a design parameter. The first consequence: every component must be deliverable through the cenote opening's dimensions at the coordinating system's specified delivery geometry, by the heavy lift unit's aerial tether, into a water surface that is floating at whatever height the water table currently occupies. The delivery is not to a platform. It is to the water. The water receives the component and the swarm takes it from there. The heavy lift unit does not need to know the water's current height. The tether length accommodates the water table's full seasonal range as a standard parameter in the delivery geometry calculation. The second consequence: every component must achieve neutral buoyancy in the cenote water before any permanent connection is made. A component that sinks upon delivery, denser than the water it displaces, requires the swarm to hold it at depth against gravity until the ballast system is installed and operational. A component that floats, less dense than the water it displaces, requires the swarm to hold it at depth against buoyancy. In either case, the swarm's holding force is the component's weight or buoyancy difference from neutral, and the swarm unit's battery life is the holding time limit. The jigsaw architecture's requirement that each component achieve neutral buoyancy before anchoring is not an abstract principle. It is a swarm battery life constraint expressed as a design requirement. Components that require swarm force holding for the full duration of the assembly sequence drain swarm batteries faster than the construction schedule allows. The neutral buoyancy specification for each component, the ballast tank sizing and fill protocol that produces a specific component mass at a specific water density, is calculated by the coordinating system before the component is fabricated. The cenote's water density is known from the halocline sensor network salinity measurements at the delivery depth. The component's displacement volume is known from the design geometry. The neutral buoyancy ballast fill is calculated as the difference between the component's mass and the displaced water mass. The ballast tank is sized and filled to this calculation. The component arrives at the cenote opening at the correct ballast state for neutral buoyancy at the delivery depth's water density on the day of delivery. If the water table has risen or fallen since the ballast fill was calculated, if the delivery depth's effective water density differs from the calculation's assumption because the halocline has migrated, the component's buoyancy state on delivery will deviate from neutral. The swarm compensates with temporary holding force while the coordinating system's ballast management protocol adjusts the ballast fill to the current water density. The adjustment is small. Halocline migration within the trial window's observed range produces water density variations small enough that the required ballast adjustment is within the ballast system's rapid fill capacity. The component is at neutral buoyancy within minutes of delivery. The swarm's holding force requirement ends when the adjustment completes. This is autonomous construction, the coordinating system detecting a parameter deviation from the delivery plan, calculating the compensation required, issuing the ballast adjustment instruction to the component's management system, and confirming neutral buoyancy from the component's sensor return, all without Terraform operator intervention, because the deviation and the compensation are within the parameters the Terraform operator's phase authorization specified. The operator authorized delivery at this location under these trial window conditions. The coordinating system manages the delivery-specific execution within those authorized conditions autonomously. The jigsaw as construction algorithm. The jigsaw architecture's surface description: every component sized to the heavy lift payload limit, assembly sequence identical to structural sequence, final closure element making the module self-supporting, understates its function as a construction algorithm. The jigsaw is not just a way of making a large structure from smaller deliverable pieces. It is a way of making each construction step an irreversible commitment to the step's quality before the next step depends on it. The traditional construction sequence in the surface world separates construction from quality verification. The contractor builds, the inspector verifies, defects identified by verification are remediated, the verified section is accepted, and the next section's construction begins. The verification is external to the construction, a separate activity performed by separate personnel after the construction is complete. This sequence has a well-documented failure mode. Defects that are expensive to remediate after adjacent construction has proceeded are pressured toward acceptance under schedule or cost constraint, because the remediation cost compounds when it requires removing or modifying completed adjacent work to access the defect. The jigsaw architecture makes the quality verification internal to the construction sequence in a specific way. The module becomes self-supporting only when the final closure element is installed and the joint polymer at every panel connection has cured to its specified strength. Before the closure element, the module is a partially assembled structure whose integrity depends on the swarm's holding force. The closure element converts the structure from swarm-supported to self-supporting in a single step. The conversion is the quality verification. If any joint in the assembly has not cured to the strength that makes the panel geometry self-stable, the conversion fails. The module does not become self-supporting when the closure element is installed. The failure is immediately observable. The module deflects. The joint polymer's color change indicator, specified in the polymer formulation for exactly this purpose, shows at the uncured joint, and the coordinating system's structural sensor network identifies the deflection source from the differential response of the piezoelectric sensors at each joint. The jigsaw's self-supporting conversion is not a quality test administered after construction. It is an integral step in the construction sequence whose successful completion is the construction sequence's quality verification. A module that converts successfully to self-supporting has passed its quality verification as a consequence of the assembly sequence's physics. A module that does not convert successfully has identified its own defect before any adjacent construction depends on it. This is the jigsaw's second function beyond aerial delivery accommodation. It sequences the construction so that quality is verified at each step before the next step begins, without requiring an external verification activity, because the construction sequence's physics is the verification. The coordinating system's construction management layer implements the jigsaw as a step-gated process. Each step in the assembly sequence has a completion criterion that must be satisfied before the coordinating system issues the instruction to begin the next step. The completion criterion for each panel installation is the joint polymer's cure conformation, the polymer's electrical conductivity change that the cure chemistry produces and that the joint interface's embedded sensor detects and reports through the crystal tube section's data conduit. The completion criterion for the closure element installation is the structural sensor network's confirmation that the module's deflection under the swarm's release of holding force is within the design tolerance for a self-supporting assembly. The completion criterion for the ballast system activation is the halocline sensor network's confirmation that the module's depth is within the neutral buoyancy target range. Each step waits for the previous step's completion criterion before beginning. The construction sequence is step-gated by sensor confirmation, not by schedule. The coordinating system does not advance the construction sequence on a time estimate. It advances on a confirmation. If the confirmation is delayed, if the joint polymer's cure is slower than the temperature model predicted, if the module's deflection at swarm release exceeds the tolerance and requires joint remediation, the construction sequence waits. The schedule extends. The quality does not compress. A construction sequence that waits for quality confirmation at every step before advancing is not a slow construction sequence. It is a construction sequence whose rework rate approaches zero, because defects that would have compounded through subsequent steps without the step gate are identified and addressed before they compound. The time the step gates cost in nominal schedule is recovered in rework elimination. The nominal schedule is longer. The actual schedule, including the rework that the step gates prevent, is shorter. The quality discipline is the schedule discipline. How the swarm thinks. The swarm is not a collection of robots thinking in parallel. It is a collection of actuators executing a choreography the coordinating system composes and updates in real time. The choreography is not written in advance of the construction sequence. It is generated by the coordinating system's construction management layer from the component delivery sequence, the assembly sequence determined by the jigsaw architecture's structural logic, the current swarm unit positions, the current battery states, the current sensor readings from the partially assembled module's structural sensor network, and the geological model's current characterization of the cenote volume in which the assembly is occurring. All of these inputs change as the construction sequence progresses. The choreography is not a fixed score. It is a continuous improvisation by the coordinating system against a changing environment, executed by units that follow the current instruction set without needing to understand the improvisation's overall logic. This is computationally demanding in the obvious sense. The coordinating system is simultaneously maintaining the geological model, monitoring the structural sensor network, tracking swarm unit positions and battery states, managing the heavy lift unit's delivery schedule, and composing the next instruction set for each swarm unit, at the update rate the construction sequence's pace requires. The computational demand is why the coordinating system's hybrid classical quantum mesh, the high-volume classical compute layer managing logistics and scheduling, the quantum interference nodes managing long-horizon pattern recognition, was specified to support the construction management function alongside the biological management, the transit scheduling, and the governance operations that run concurrently. The swarm's response to unexpected conditions illustrates the choreography's character. During a standard panel positioning sequence, the coordinating system issues position and orientation instructions to the positioning units holding the panel in the assembly zone. The panel's current position and orientation are reported by the positioning unit's sensor arrays. The coordinating system calculates the difference between current and target position. The instruction set moves the positioning units by the calculated difference. The panel arrives at target position. The joint sealing units move to the joint interface and begin the polymer application sequence. If a current event, an underground river pulse, a seismic signal from the fracture network, a biological community response to the construction activity, introduces a force on the panel during the joint sealing sequence, the panel's position deviates from target. The positioning unit's sensor arrays report the deviation. The coordinating system calculates the compensation force required. The instruction set adjusts the positioning unit's force application. If the compensation force exceeds the positioning unit's battery reserve capacity, if the current event is large enough that maintaining panel position through it would drain the positioning units before the joint seal is complete, the coordinating system aborts the sealing sequence, withdraws the joint sealing units, instructs the positioning units to return the panel to the neutral buoyancy staging position, and logs the abort event with the current event sensor data. The abort is not a failure. It is the correct response to conditions that exceeded the construction sequence's safe operating parameters. The panel is undamaged. The joint sealing units have not applied polymer to a joint that will fail to cure correctly because it was displaced during application. The construction sequence restarts when the current event's force has subsided to within the positioning unit's capacity range. The coordinating system's geological model updates the current event's characterization from the sensor data recorded during the abort event. The next positioning attempt is better calibrated for the current event's force profile. The swarm does not know why it aborted the sealing sequence. The swarm executes the abort instruction. The coordinating system knows why. The construction record logs what happened. The digital twin learns from it. The next attempt improves. The anchor is conversation. The anchor sequence is the most consequential construction operation in the founding module's deployment. It is the moment the structure commits to the formation, the moment the floating question becomes the anchored answer. Everything about the anchor sequence is designed to ensure that the commitment is made correctly once rather than approximately many times. The anchor pylon's ground-penetrating acoustic sensor, mounted at the pylon's tip, active throughout the driving sequence, is the conversation's medium. The sensor emits acoustic pulses that penetrate the limestone ahead of the pylon tip. The returns characterize the limestone stratigraphy, the density, the porosity, the fracture orientation, the dissolution void distribution, the presence of any geological feature that would make the planned anchor location unsuitable for the load the crystal tube standard structural calculations require at that point. The coordinating system's geological model has characterized the cenote wall at the proposed anchor location from the Hydroprint campaign's acoustic survey and the Pathfinder unit site characterization. The model has specified the anchor location based on its prediction of the limestone structural competence at that location. The pylon's ground-penetrating sensor confirms or revises this prediction as the pylon advances toward the limestone. Before any permanent contact is made, the sensor has told the coordinating system whether the limestone at this specific location matches the model's prediction. If it matches, if the sensor stratigraphy characterization is consistent with the model's prediction and the model's prediction supports the required anchor load, the driving sequence proceeds. The hydraulic ram applies the specified seating force. The ground-penetrating sensor monitors the force transmission through the limestone as the pylon advances, confirming that the force is distributing through competent rock rather than through a dissolution void that would produce a point load failure. The fast-cure marine polymer grout flows through the secondary conduit behind the tip, filling the annular space between pylon and limestone, displacing water, beginning cure in contact with the limestone's calcium carbonate surface chemistry that the grout formulation was designed to bond with. If it does not match, if the sensor returns a stratigraphy that differs from the model's prediction in ways that affect the anchor location's structural competence, the driving sequence halts. The coordinating system analyzes the deviation, updates the geological model, identifies the nearest alternative anchor location that the updated model supports, repositions the pylon to the alternative, and begins the confirmation sequence again at the new location. The anchor sequence has no maximum permitted deviation from the planned location. There is no plan that the formation must accommodate. The anchor goes where the formation says it can receive the load. The plan specifies an initial target. The formation specifies the actual location. This produces anchor patterns that differ from the engineering drawings the coordinating system's pre-construction model generated. The anchor pattern on the as-built record, the digital twin's construction layer, is the anchor pattern the formation specified, not the anchor pattern the pre-construction model planned. The two patterns are similar where the Hydroprint survey characterized the formation accurately and different where the formation's actual limestone stratigraphy diverged from the Hydroprint's acoustic prediction. The difference between the planned pattern and the as-built pattern is a record of where the hydroprint survey's resolution was insufficient, where the pre-construction characterization missed features that the anchor sequence's ground-penetrating sensor found. Every difference between planned and as-built is a data point that improves the hydroprint methodology for the next installation. The hydroprint's acoustic sensor configuration is revised to provide better resolution at the spatial scale that the as-built record identifies as the planning versus reality gap. The next installation's pre-construction model is more accurate at those spatial scales. The anchor sequence's conversations with the formation reveal less deviation from the updated model. The dialogue between the construction sequence and the formation gradually converges toward a pre-construction model accurate enough that the anchor sequence's conversations with the formation are confirmations rather than revisions. The dialogue is never complete. The formation always knows more about itself than the acoustic survey can detect. But each installation cycle advances the model's accuracy, and each advance reduces the deviation between planned and as-built, and each reduction increases the construction efficiency of the next cycle. The construction sequence that builds the infrastructure is simultaneously the research program that improves the next construction sequence. What happens in the night window? The heavy lift unit operates in timed windows: early morning, low wind, low tourist traffic, minimum biological acoustic demand from the coordinating system's scheduling constraint. The window is finite. The heavy lift unit delivers one primary structural component per sortie. The window accommodates a defined number of sorties. Between windows, no heavy lift activity. The swarm works. The interwindow period is when the swarm's independent operational capacity matters most. A panel delivered in the first window's final sortie may be in the joint sealing sequence's midpoint when the second window opens and the next panel delivery is imminent. The joint sealing sequence cannot be interrupted for the delivery. The polymer's cure chemistry has a time window within which the joint interface must be held at the correct geometry for the cure to produce the specified bond strength. An interruption that moves the panel before the cure window closes produces a substandard joint that the commissioning unit's verification survey will flag. The coordinating system's delivery scheduling ensures that the joint sealing window for any panel that the swarm has begun sealing is complete before the next delivery is staged for the swarm's reception. The heavy lift unit's sortie timing is calculated against the swarm's estimated joint sealing completion time, with margins for the geological model's uncertainty in the cenote's current event frequency. The delivery window and the swarm's construction sequence are synchronized by the coordinating system so that the heavy lift unit and the swarm are never competing for the swarm's attention. This means some deliveries wait in the heavy lift unit staging queue while the swarm completes the preceding joint sealing sequence. The heavy lift unit hovers above the cenote opening with the next panel on the tether, holding position until the coordinating system's confirmation that the previous panel's joint has cured and the swarm is in reception position. The wait is on the heavy lift unit's schedule, not on the swarm's sequence. The swarm works through the interwindow nights without the heavy lift unit's deliveries. The interwindow period is when the swarm performs the operations that the heavy lift delivery windows crowd out of the daytime schedule: the joint cure monitoring, the structural sensor calibration, the ballast system adjustment, the biological census operations that the construction activity suppresses during the delivery window, the acoustic transceiver chain integration testing for sections installed in the previous window. The swarm does not rest between delivery windows. It uses the interwindow period for the construction sequence's quality assurance operations that the delivery window's pace does not permit during delivery. A construction sequence that uses its downtime for quality assurance rather than rest is a construction sequence that does not separate construction from quality management. The swarm is always either constructing or verifying the quality of what it has constructed. The quality management is not a separate phase after construction. It is the construction sequence's continuous background operation, advancing through the verification checklist for each installed component while the foreground operation, the delivery reception, positioning, and sealing, advances through the assembly sequence. The stacking decision. The founding module's successful neutral buoyancy monitoring, the trial window's satisfactory conclusion, produces the Terraform Operators anchor commitment authorization. The authorization releases the coordinating system to begin the anchor sequence. The anchor sequence commits the founding module to the formation. The second tier's construction can begin at the founding module's trial window conclusion. The formation model has been sufficiently populated by the founding module's sensor data that the second tier's trial window requirement is reduced from the founding module's minimum. But beginning the second tier's construction immediately on the founding module's authorization is not necessarily the correct decision. The stacking decision is the judgment of when the formation model's current state justifies committing to the second tier. The stacking decision is not the Terraform Operator's unilateral judgment. It is the coordinating system's readiness signal, the formation model's stability indicator reaching the threshold that the founding charter specifies for second-tier authorization, confirmed by the Terraform Operator's concurrent authorization that the signal is consistent with the formation data the Terraform Operator's direct observation has produced during the trial window. The coordinating system's signal is necessary. The Terraform Operator's concurrence is sufficient. Neither alone is the authorization. The formation model's stability indicator is not a single measurement. It is a composite of multiple model layers stability, the structural stability model's confidence in the anchor pylon load distribution across the seasonal cycle, the halocline model's seasonal depth range bound, the biological succession model's colonization rate at the founding module's surface area, the acoustic baseline seasonal pattern characterization, and the flow velocity model's flood risk assessment across the trial window's hydrological range. Each model layer has its own stability metric. The composite stability indicator is the minimum of the layer stability metrics. The stability of the least stable model layer determines the composite. The founding module's second-tier stacking decision in a typical formation cenote installation occurs between 3 and 6 months after the first anchor commitment, significantly less than the founding module's own 12-month minimum trial window, but not immediately on anchor commitment. The reduced duration reflects the reduced information deficit. The second tier's geological conditions are the same cenote formation the founding module's trial window has already characterized. The reduction is not proportional to the trial window duration, because the information gained in the trial window's first months is higher per unit time than the information gained in its final months. The early data establishes the seasonal baseline, the late data confirms its stability. The second tier benefits from the established baseline without needing the time to establish it. Each subsequent tier reduces its pre-construction readiness period further, as the formation model's confidence in the cenote's behavior under occupied load deepens with each season of operation. The fourth tier may proceed within weeks of the third tier's anchor commitment. The 10th tier may proceed within days of the 9th tier's anchor commitment. The formation model at that stage is mature enough that each new tier's incremental load addition is a small perturbation to a well-characterized system whose response the model can predict at high confidence from existing data. The compression of the readiness period is not impatience. It is efficiency, the correct allocation of waiting time to the period when waiting produces information, and advance to the period when the information is sufficient for advance. A civilization that applies the same waiting time to its 100th tier that it applied to its founding module is a civilization that has not learned from what the trial windows produced. The waiting is for learning. When the learning is sufficient, advance is appropriate. The founding charter's patience is not a permanent pace. It is the pace appropriate to the information deficit. As the deficit closes, the pace increases. The Autonomous Commissioning Survey. The Commissioning Unit's Verification Survey, the post-installation quality verification that Chapter 1 documented as the core's operational accountability mechanism, is itself an autonomous operation. The Commissioning Unit executes the survey protocol from the Coordinating System's verification instruction set, without Terraform Operator supervision of individual verification steps, and returns the survey results to the Coordinating System's quality management layer for evaluation against the Crystal Tube Standards pass/fail thresholds. The survey protocol has no discretion. Every crystal tube section receives the same verification sequence regardless of the installation conditions the installation units reported during the construction sequence, regardless of whether the construction sequence ran smoothly or required abort and restart cycles, regardless of how the halocline sensor network's data during the installation period compared to the geological model's prediction. The verification protocol does not assume good construction. It verifies each quality parameter independently. The optical transmission measurement, the commissioning unit's light source illuminates the tube wall at the wavelength range the crystal specification uses. The photodetector on the opposing side of the tube measures the transmitted fraction. The ratio is compared to the crystal specification threshold for the tube section's depth zone. Pass or fail. The piezoelectric sensor calibration, the commissioning unit generates a known acoustic pulse at a known location in the tube wall. The coordinating system reads the response from every piezoelectric sensor in the newly installed tube section. The response pattern is compared to the calibration model for a correctly installed sensor network in a tube of this geometry and material. Deviations from the calibration model that exceed the tolerance identify sensors that are incorrectly embedded, damaged during installation, or connected to a data bus that is not communicating correctly with the coordinating system's monitoring layer. Pass or fail for each sensor. Aggregate pass or fail for the sensor network. The acoustic transceiver integration, the commissioning unit pings each transceiver node in the newly installed section from the crystal tube network's data conduit. The node responds with its identification, its position fix, its signal quality to adjacent nodes, and its battery state. The coordinating system's acoustic mapping layer integrates the new node's position fixes with the existing network's node positions, confirming that the new section's nodes are extending the network's coverage in the geometry the installation plan specified. Pass or fail. The biological baseline sampling, the commissioning unit's water chemistry sampler collects samples at the depth stations the crystal tube standard specifies for a new section. The samples are analyzed by the onboard sensor package, dissolved oxygen, salinity, H2S concentration, dissolved organic carbon, key mineral ion concentrations, against the baseline the coordinating system's geological model predicts for the cenote at the section's depth. Significant deviation from prediction triggers a Terraform operator notification and a biological census subdeployment to the section before the first guest transit. Minor deviation within the prediction's uncertainty range is logged as a baseline data point and incorporated into the digital twin's water chemistry model. The deviation magnitude determines the response. The coordinating system's quality management layer receives the commissioning unit's survey results and generates the pass/fail determination for the section. A section that passes all 4 verification categories is released to the Crystal Tube Standards operational inventory. A section that fails any category is flagged for remediation. The specific failure category determines the remediation instructions that the coordinating system issues to the relevant unit type. Optical transmission failure triggers installation unit redeployment for panel replacement. Piezoelectric sensor failure triggers sensor replacement at the failed sensor locations. Acoustic transceiver failure triggers transceiver node replacement at the failed nodes. Biological baseline deviation triggers biological census and potentially a water chemistry intervention by the Biological Management Protocol. Remediation is not exceptional. It is the designed response to the quality management process identifying a deviation from specification. The construction sequence is designed to identify deviations before they propagate. The commissioning unit's survey is the final checkpoint before propagation, the last opportunity to correct a deviation before the section enters service, and the deviation's consequences are no longer limited to the section itself. A section that enters service with a substandard optical transmission has a substandard optical transmission for the duration of its service life, degrading guest experience, biological monitoring fidelity, and the formation legibility that the crystal specification is designed to protect. The commissioning unit's survey prevents this outcome by identifying the deviation before service and requiring remediation before release. The autonomous commissioning survey is the quality management process that makes autonomous construction trustworthy. The construction is autonomous. The quality management is autonomous. The trustworthiness comes from the quality management's independence from the construction. The commissioning unit has no relationship to the installation unit whose work it is verifying. It is a different unit type, executing a different protocol, accountable to the coordinating system's quality management layer rather than to the construction management layer. The construction and the verification are separate activities, executed by separate units, governed by separate protocols, reporting to separate management layers within the same coordinating system. The construction cannot certify its own work. The verification certifies the construction. The autonomous construction earns trust because the autonomous verification is independent of it. The coordinating system's construction intelligence. The coordinating system's construction management layer is not a planning tool that generates a plan and monitors its execution. It is a continuous decision system that generates the next instruction for each unit from the current state of all units, the current state of the formation model, and the current state of the construction sequence, in real time, at every update interval. The distinction matters because a planning tool's plan is fixed at plan generation time. When the formation deviates from the plan's assumptions, when an abort event occurs, when a sensor reading shows a condition the plan did not anticipate, when a unit failure removes a capability the plan depended on, the plan requires human revision. The human Terraform operator must review the deviation, assess its implications, and revise the plan before the construction sequence can continue. The coordinating system's continuous decision function does not have a plan to revise. It has a current state and a decision rule. The decision rule generates the next instruction from the current state. When the formation deviates from the model's prediction, when an abort event occurs, when a sensor reading shows an anomalous condition, the coordinating system's geological model updates with the anomalous sensor data, the updated model generates a new current state, and the decision rule generates revised instructions from the new current state. The construction sequence adapts in real time without the plan revision cycle that the planning tool requires. This does not eliminate the Terraform operator from the construction management process. It relocates the Terraform operator to the decisions that require human judgment, the phase threshold authorizations, the geological anomaly assessments whose implications the coordinating system's model cannot bound within the founding charter's safety parameters, the concurrent authorization for any construction deviation that falls outside the autonomous decision rule's authorized parameter range. The authorized parameter range is the governing principle. The coordinating system operates autonomously within the parameter range the Terraform operator's phase authorization established. The coordinating system requests Terraform operator review for any condition outside the authorized range. The Terraform operator does not supervise every construction decision. The Terraform operator defines the decision space within which the coordinating system operates autonomously. This is the correct division of cognitive labor between the human judgment that the founding charter's safety architecture requires and the computational intelligence that the construction sequence's pace and complexity require. The human cannot supervise every instruction in a swarm construction sequence operating across multiple active construction fronts simultaneously. The instruction frequency exceeds the human supervision bandwidth by several orders of magnitude. The human must supervise the decisions whose consequences are outside the parameter range that autonomous decision can safely explore. The authorized parameter range is the agreement between human judgment and autonomous decision about which decisions are safe to delegate. The construction sequence that results is faster than human-supervised construction, more responsive to formation feedback than plan-unrevised construction, and safer than unsupervised autonomous construction. Because the parameter range that gates Terraform operator review is calibrated to the formation's known behavior range and the construction equipment's known failure mode range. Within the known range, the coordinating system decides correctly. Outside the known range, the Terraform operator decides whether to extend the known range or halt until the unknown condition is characterized. The construction intelligence is the coordinating system's intelligence, shaped by the parameter range the Terraform operator establishes, operating at the speed the formation's conditions require. The building that builds itself. The phrase from Part IV's title, "Machines that build themselves," is not fully accurate for the construction sequence documented in this chapter. The founding module does not build itself. The robot frontier core builds the founding module. The coordinating system orchestrates the core. The Terraform operators gate the sequence's phase transitions. The heavy lift unit delivers the components. The swarm assembles them. The commissioning unit verifies the assembly. The formation accepts the result. But the phrase captures something true about what the construction sequence looks like from outside its own logic: a formation that was empty before, now containing an inhabited structure, and no human having entered the formation to build it. The human beings who authorized the construction were at the surface. The human beings who will inhabit the construction are at the surface. The construction itself occurred in a space that no human was present to supervise, by equipment that received its instructions from a system no human was operating moment to moment, within a quality management framework that no human was overseeing continuously. From the outside, the building built itself. From the inside, the building was built by the civilizational infrastructure, the coordinating system, the core, the Terraform operator's authority, that makes construction in the cenote possible without requiring human presence in the cenote during construction. This is what autonomous construction achieves in the PipeDream context, not the replacement of human intelligence with machine intelligence, but the deployment of each type of intelligence where it is most effective. Machine intelligence at the instruction frequency and sensor monitoring density that the construction sequence requires. Human intelligence at the threshold decisions whose consequences exceed the authorized parameter range. The construction proceeds at machine speed. The safety architecture operates at human judgment quality. The two are not in conflict because they are not competing for the same decisions. The building builds itself in the sense that matters operationally. The human beings who will live in it did not build it by hand. The machines that did build it did so within a framework of human authority that shaped every parameter the autonomous construction operated within. The formation provided the space. The machines built the structure. The humans authorized the parameters and gated the phases. The coordinating system made the 10,000 decisions per construction hour that none of the humans could have made and none of the machines could have judged. The building that builds itself is the product of that specific combination. Remove any element and the combination fails: no core, no construction capability in the cenote, no coordinating system, no construction intelligence at the required pace, no Terraform operators, no safety governance at the threshold decisions, no formation, no cenote to build in. The building that builds itself because everything that is needed for it to build itself is in the right place, doing the right work, at the right pace, governed by the right authority. That is not a machine achievement. It is a civilizational one. Cross-references: Part 1, CH3, PipeDream begins, Part 1, CH4, floating before anchoring, Part 2, CH4, the crystal tube standard, Part 2, CH5, growing one module at a time, Part 3, CH3, linking cenote to cenote, Part 4, CH1, the robot frontier core, Part 4, CH3, maintenance without humans, Part 4, CH4, swarm engineering, Part 7, CH1, breakaway architecture. For step-gate completion criteria and sensor confirmation thresholds, see Appendix D, Construction Operations Manual. For stacking decision readiness signal composition and Terraform operator concurrent authorization protocol, see Appendix H, Governance Operations Manual. For commissioning unit survey protocol and pass/fail threshold specifications by depth zone, see Appendix D, Construction Operations Manual. For coordinating system authorized parameter range definition and Terraform operator review trigger conditions, see Appendix H, Governance Operations Manual. PipeDream. Part 4, Machines that build themselves. Chapter 3, Maintenance without humans. Maintenance is the part of construction the surface world defers until after the building is occupied and the construction budget is spent. The design team moves on. The contractor demobilizes. The occupants arrive. 6 months later, the first component fails. The maintenance team, funded by an operating budget that was set before anyone knew what the actual failure rate would be, staffed by technicians who were not present during construction and do not have access to the original design rationale, equipped with the tools that fit within the maintenance budget rather than the tools the design required, responds. The response addresses the symptom. The underlying condition that produced the symptom is typically not in the maintenance team's technical scope, not legible from the surface the team can access, and not documented in the maintenance manual because the design team did not anticipate it. The surface world's maintenance paradigm is reactive, underfunded, staffed with insufficient design knowledge, and structurally disconnected from the construction phase that determined what the maintenance would need to address. These are not failures of individual projects. They are the structural outcomes of a development model that treats maintenance as the building's future problem rather than the design's current responsibility. PipeDream's maintenance paradigm was specified before the founding module's first panel was fabricated. Not the maintenance procedures, the maintenance philosophy, the commitment that every component in the installation would be maintainable without specialized design knowledge, by technicians working in the conditions the installation actually presents at the time of maintenance need, with tools they can carry in a maintenance sub, using replacement cartridges that are stored at the nearest hub and are identical to the cartridges that will be available at any future maintenance interval across the full 1,000-year design life. The maintenance philosophy preceded the design. The design was constrained by the maintenance philosophy. Every component that could not meet the maintenance philosophy's requirements was redesigned until it could, or replaced with a component whose architecture was compatible with the maintenance conditions from the start. This is the inversion the surface world's development model never achieves, maintenance as a design input rather than a design afterthought. The building designed for maintenance performs differently than the building that maintenance is later applied to. The difference is not in the maintenance operations themselves. It is in whether the building was built for those operations. The condition-based maintenance model. The surface world's maintenance scheduling operates on two models, time-based and failure-based. Time-based maintenance replaces components at defined calendar intervals regardless of their actual condition. The lubricant is changed every 6 months whether it needs it or not. The filter is replaced every quarter whether it has reached its capacity or not. The bearing is inspected annually whether any observable symptom suggests impending failure. Time-based maintenance is predictable and administrable but wasteful. Most replacements occur before the component has consumed its useful service life, and the interval is set conservatively enough to prevent failure in the worst-case service conditions, which means most components in typical service conditions are replaced far earlier than their actual condition warrants. Failure-based maintenance waits for failure and responds. It is simple to implement, no scheduling required, the failure announces itself, and catastrophically expensive when the failing component is deep in the installation's infrastructure and its failure cascades into adjacent systems before the response arrives. Failure-based maintenance is not a philosophy. It is the absence of a philosophy, producing the expensive emergency response that the surface world's maintenance programs are perpetually funding. PipeDream's maintenance model is condition-based. Every component in the installation is maintained when its actual measured condition indicates maintenance is needed, not before and not after. The condition measurement is continuous. The coordinating system sensor network monitors every maintainable component at the sampling frequency appropriate to that component's failure mode's progression rate. The maintenance trigger is the measured condition crossing the threshold the coordinating system's maintenance protocol specifies for that component type, not the calendar interval and not the failure event. The condition-based model requires that every maintainable component has a measurable condition indicator whose value changes predictably as the component's service life is consumed. The crystal specification's optical transmission coefficient is the measurable condition indicator for the crystal tube wall panels. The joint polymer's electrical conductivity is the measurable condition indicator for the structural joints. The halocline sensor network salinity readings are the measurable condition indicators for the halocline zone's material performance. The rate of change in the readings identifies chemical attack on vulnerable materials before the attack has consumed structural capacity. The streaming potential harvest network's power output is the measurable condition indicator for the anchor bracket conductive coating's integrity. Every component whose failure mode produces a measurable precursor condition is a component that can be maintained condition-based. The design goal was to ensure that every component in the installation has such a precursor, that the installation has no components whose first observable indication of degradation is catastrophic failure rather than measurable condition decline. The ALON panels at the anoxic boundary are the exception that proves the rule. ALON's failure mode, catastrophic shear without the crazing precursor that chemically strengthened glass provides, is the installation's only failure mode without a directly observable progressive indicator. The response to this exception is not acceptance of the failure mode's risk. It is compensatory monitoring density. The ALON panel zones carry the installation's highest sensor density, the shortest sampling intervals, the most frequent commissioning unit inspection schedule, and the only component type in the installation that the coordinating system escalates to Terraform operator review on any anomalous reading regardless of the anomaly's magnitude. The monitoring compensates for the precursor's absence by reducing the interval between potential onset and detection to below the interval at which an undetected degradation event would propagate beyond the affected panel before the passive hydraulic rotary gate's Venturi response could isolate the section. The ALON exception confirms the design philosophy, where condition-based maintenance cannot rely on a measurable precursor. The monitoring density is increased until the effective early warning time is equivalent to what the precursor provides for other component types. The maintenance model's condition-based principle applies to all components. The monitoring architecture compensates for the components that do not naturally provide precursor signals. Biological maintenance as primary infrastructure. The coordinating system's maintenance scheduling distinguishes between two categories of maintenance operation: mechanical maintenance, performed by the robot frontier core's maintenance unit types and by human technicians where the cartridge swappable principle requires human access to the maintenance aisle, and biological maintenance, performed by the living systems the installation manages as maintenance infrastructure. Biological maintenance is not a supplement to mechanical maintenance. It is the primary maintenance layer, the maintenance system that operates continuously, at zero marginal cost per operation, at spatial coverage and response time that mechanical systems cannot match, across the full installed surface area of the crystal tube network simultaneously. The ancestral vitreous cleaning colonies in the freshwater zone are not auxiliary equipment. They are the crystal specification's primary enforcement mechanism. A crystal tube section in the freshwater zone without an active ancestral vitreous colony management program would lose crystal specification compliance within weeks of the last mechanical cleaning. The biofilm accumulation rate in the freshwater zone's warm, nutrient-rich water is too high for any mechanical cleaning schedule that does not itself consume the cleaning equipment's full operational capacity. The mechanical cleaning schedule that would maintain crystal specification without the biological maintenance layer is not economically viable. The biological maintenance layer makes it economically viable by reducing the mechanical cleaning frequency to the intervals at which the biological layer's capacity is insufficient for the specific fouling load in that section. The acoustic transponder network that steers the ancestral vitreous schools is not a biological management tool. It is the crystal specification's maintenance scheduling system, routing biological maintenance capacity against the optical transmission gradient across the freshwater zone's full panel inventory. The coordinating system that manages the transponder network is not managing fish. It is managing maintenance coverage. The squeegeebot fleet in the halocline and saltwater zones performs the same function below the biological lethal limit where the ancestral vitreous colonies cannot operate. The squeegeebots are not a replacement for the biological maintenance layer. They are the biological maintenance layer's mechanical equivalent, deployed in the zone where biology cannot operate, executing the same maintenance function, optical surface cleaning to crystal specification, by mechanical means rather than biological ones. The coordinating system does not distinguish between biological and mechanical maintenance units in its maintenance coverage allocation. It allocates cleaning capacity against optical transmission demand. The cleaning capacity happens to be biological in the freshwater zone and mechanical in the halocline and saltwater zones. The allocation algorithm does not know this. It knows this panel's optical transmission is at threshold X, and cleaning capacity unit Y, biological or mechanical, is closest to it. The unit receives the routing instruction. The instruction does not specify how the unit cleans. The unit cleans by the mechanism its design provides. This integration is the biological-mechanical hybrid maintenance architecture that the founding engineers designed by never separating the two. The surface world separates them. Mechanical maintenance is engineered infrastructure managed by facilities management. Biological management is environmental health managed by the biology department. The two operate on separate schedules, are managed by separate personnel, and never discuss whether they are both optimizing for the same outcome. PipeDream's coordinating system manages both as a single maintenance function because both are producing the same outcome, crystal specification compliance, and optimizing one without the other produces suboptimal coverage at higher total cost than optimizing both together. The MYCO filtration maintenance cycle. The gray water processing gallery's mycofiltration panels, the mycelium-based filtration lining that metabolizes surfactants, dissolved food residues, and personal care compounds from the installation's gray water stream, are the installation's self-maintaining maintenance component. They consume the material they are maintained to remove. They reproduce the filter medium they are composed of. They harvest and provide soil amendment as a byproduct of performing their filtration function. The mycofiltration panel's maintenance cycle is the biological cycle of the fungal network it is composed of. The network grows through the panel substrate, consuming the substrate's nutrients as it extends. When the substrate is consumed, when the fungal network has processed the substrate's available nutrition, the network requires fresh substrate to continue growing. The panel harvest cycle removes the mature network sections and applies them as food forest soil amendment. The panel replacement cycle installs fresh substrate for the new network sections to colonize. The replacement substrate is not manufactured. It is produced by the installation's own waste streams, the food forest's leaf litter and root turnover, combined with the coarser fraction of the black water digestate solid output after the liquid fraction has been separated for the food forest irrigation header. These two waste streams, combined in the ratio the coordinating system's substrate preparation protocol specifies, produce the mycofiltration panel substrate at zero external material cost. The mycofiltration panel's maintenance cycle is: the panel processes gray water, the panel's fungal network grows, the mature network is harvested as soil amendment, the substrate is replaced from the installation's internal waste streams, the new fungal network colonizes the fresh substrate, the panel processes gray water. The cycle has no external input and no waste output. Every material that enters the cycle is consumed within the cycle. The panel maintains itself from the waste streams it is installed to process. The coordinating system's maintenance scheduling for the microfiltration panels tracks the fungal network's metabolic activity through the gray water chemistry. The water chemistry downstream of the panels reflects how effectively the fungal network is processing the incoming gray water load. When the downstream chemistry shows increasing surfactant or dissolved organic carbon concentrations, indicating that the fungal network's processing capacity is declining as the substrate is consumed, the coordinating system schedules the harvest and substrate replacement cycle. The condition indicator is the water chemistry. The maintenance trigger is the water chemistry crossing the threshold. The threshold is set at the point where incoming gray water quality decline would, if unaddressed, begin to degrade the ballast circuit's water quality below the specification the ballast management protocol requires. The maintenance trigger is always ahead of the point where the panel's declining function affects the downstream system. The condition-based maintenance model ensures that the microfiltration panel's maintenance cycle runs when the panel needs it, not when the downstream system is already suffering the consequences. The anchor pylon inspection protocol. The anchor pylons are the installation's most critical structural components and the least accessible to mechanical maintenance. The stainless steel pylons in the freshwater zone can be accessed by a maintenance sub descending to the anchor depth along the crystal tube network's guide rail. The in-canal pylons in the anoxic zone require an alone-paneled maintenance gallery approach. The maintenance sub cannot operate in the anoxic zone's hydrogen sulfide chemistry without the protective enclosure the alone panels provide. Neither access route permits mechanical disassembly of the pylon in place. The pylon's connection to the limestone, the fast-cure marine polymer grout that the anchor sequence injected through the secondary conduit behind the pylon tip, is a permanent bond whose mechanical disassembly would require fragmenting the surrounding limestone to expose the grout interface. Fragmenting the limestone around a structural anchor is not a maintenance operation. It is a demolition operation that would remove the structural capacity the anchor was providing before it was removed. The anchor pylon inspection protocol is therefore entirely non-destructive, acoustic inspection from outside the pylon's external surface, without contact with the grout interface or the limestone anchor zone. The acoustic inspection unit, a census unit variant carrying ultrasonic transducers at specific frequencies calibrated for the pylon material and the grout interface geometry, orbits the pylon at the inspection depth, emitting pulses through the pylon wall and reading the returns from the grout interface and the limestone beyond it. The acoustic returns characterize three conditions: the pylon material's integrity, the grout interface's bond quality, and the limestone stratigraphy in the anchor zone. Pylon material integrity is confirmed by the absence of discontinuities in the acoustic return from the pylon wall. Voids, cracks, or delamination would produce return signatures the coordinating system's geological analysis distinguishes from the homogeneous pylon material's characteristic return. Grout interface bond quality is confirmed by the return from the grout limestone interface. A well-bonded interface produces a specific acoustic return character that differs from the return character of a debonded interface where the grout has separated from the limestone. Limestone stratigraphy in the anchor zone is confirmed by the return from beyond the grout interface, the absence of new dissolution voids or fracture propagation in the anchor zone's limestone that the original anchor sequence's ground-penetrating characterization did not document. The inspection protocol is scheduled at the coordinating system's maintenance calendar interval for each anchor pylon depth zone, freshwater zone pylons annually, halocline zone pylons semi-annually because the halocline's chemistry is more aggressive to the fast-cure polymer grout than the freshwater zone's chemistry. Anoxic zone in-canal pylons quarterly because the H2S environment's attack on any non-in-canal component in the pylon assembly requires the highest inspection frequency regardless of the individual component's resistance. The inspection results are integrated into the digital twin structural health monitoring layer alongside the continuous piezoelectric sensor data from the crystal tube sections. The pylon inspection data and the crystal tube section data are not separate structural health records. They are two inputs to the same structural model, the model of the complete load path from the inhabited module through the crystal tube sections through the pylon to the limestone. A pylon whose acoustic inspection shows grout interface degradation is a pylon whose load path integrity is declining. The decline is visible in the digital twin structural model as a change in the model's confidence in that load path's capacity. The coordinating system allocates the monitoring resources to the declining load path's affected sections and initiates the remediation planning sequence before the load path's capacity reaches the threshold below which redistribution to adjacent pylons would be required. The remediation for a degraded pylon grout interface is injection grouting, the same polymer chemistry as the original grout, injected through a new conduit drilled by a Litho-Crustacean boring unit at the scale appropriate for the conduit geometry rather than for tunnel boring, into the degraded grout zone, restoring the bond strength. The injection grouting is performed by a maintenance unit carrying the polymer injection system and the conduit boring microorganism deployment package, the Litho-Crustacean unit scaled down to the conduit geometry, boring the injection path rather than a transit tunnel. The grout remediation is the maintenance operation that brings a degraded anchor pylon back to full structural specification without removing the pylon, without fragmenting the surrounding limestone, and without interrupting the structural function the pylon is providing during the remediation. The pylon continues bearing its load share during the remediation. The remediation augments the grout interface while the interface is still providing structural function. The structural health monitoring confirms the augmentation's effectiveness by tracking the acoustic return from the remediated zone against the pre-remediation baseline. A structural system that can be remediated while operating, by operations that do not interrupt its function, monitored continuously by sensors that confirm the remediation's effectiveness in real time, is a structural system that does not have scheduled overhaul shutdowns. It operates continuously while its maintenance occurs around it. The 1,000-year design life is achievable not because the components last 1,000 years but because the maintenance that restores them to specification can be performed without taking the system offline. The light relay maintenance. The light cannon relay system's maintenance is dominated by two failure modes, laser diode degradation and tube wall optical surface degradation. Both affect the relay's light transmission efficiency, the ratio of light power arriving at the relay's far end to the light power injected at the relay's source. The ratio decreases as the diode efficiency falls with operating hours and as the tube wall's optical surface accumulates fouling that reduces total internal reflection efficiency. The two failure modes have different maintenance responses and different maintenance triggers. Laser diode degradation is a time-based failure mode. The diode's efficiency decreases with operating hours at a rate the manufacturer's specification characterizes, and the coordinating system's power monitoring confirms in real time from the diode array's power input and the transmission measurement at the relay's far end. The ratio of these two measurements is the relay efficiency. If the far end transmission decreases relative to the power input, the efficiency has fallen. The rate of fall is the diode degradation rate. The coordinating system's maintenance calendar for diode replacement is derived from the measured degradation rate projected to the threshold below which the relay efficiency cannot maintain the light intensity the crystal specification requires at the tube section's maintenance depth. The diode array is a cartridge swappable unit. The array housing mounts to the surface tier's relay interface at a standardized connector geometry, and the replacement array is installed by disconnecting the degraded array, connecting the replacement, and confirming transmission restoration through the far end measurement. The operation requires access to the surface tier's relay interface, accessible to a technician at the cenote rim during the maintenance window. No descent required. No sub required. The most frequently replaced component in the light relay system is replaced at the cenote rim by a technician with standard hand tools. The tube wall optical surface degradation is a condition-based failure mode maintained by the biological and mechanical cleaning protocol. The same cleaning that maintains crystal specification for visual transparency maintains the internal reflection efficiency for the light relay. A tube wall that meets crystal specification for passenger visual observation also meets the surface quality standard for effective total internal reflection at the relay's operating wavelengths. The cleaning protocol that the biological maintenance layer enforces is simultaneously maintaining the visual transparency and the relay transmission efficiency. 1. Maintenance operation. 2. Functional outcomes. Where the biological and mechanical cleaning is insufficient for the relay's efficiency requirements, where a tube section's relay efficiency is below threshold even after a cleaning cycle that restores crystal specification, the problem is not the surface quality. It is the tube material's optical properties, which cleaning cannot restore. A PMMA panel whose UV stabilizer package has been exhausted may meet crystal specification for passenger visual observation. The degraded transmission is still above the passenger visual threshold, while failing the relay efficiency threshold, which requires higher transmission at the laser's specific operating wavelength than the degraded PMMA can provide at that wavelength after UV exposure has altered its spectral transmission profile. The remediation is panel replacement on the relay efficiency maintenance schedule rather than the crystal specification schedule. The relay efficiency maintenance schedule may trigger panel replacement before the crystal specification schedule does for UV-degraded PMMA in the surface tier. The earlier trigger is the correct trigger. The relay efficiency threshold is protecting the light cannon relay's function, not the passenger visual experience, and the two thresholds are not identical. The maintenance schedule that protects both functions applies the more stringent threshold. The more stringent threshold drives the replacement timing. This is condition-based maintenance applied to multiple condition indicators from the same component. The panel is maintained when the most stringent of its condition indicators reaches its threshold, regardless of which indicator that is. The component's service life is not defined by its capacity for one function. It is defined by its capacity for all functions simultaneously. The panel replacement that restores the failing function also restores the other functions that were still within threshold. The replacement is not premature for the functions that were within threshold. It is correctly timed for the function that was not. The biofilm community as maintenance partner. The biofilm community on the crystal tube walls is not a maintenance problem that the cleaning protocol addresses. It is a maintenance partner that the cleaning protocol manages. The distinction is not semantic. It reflects the ecological relationship between the biofilm community and the cleaning systems that maintain it at the crystal specification threshold. A tube wall without any biological community is a tube wall that will be colonized by whatever biological community the passage water provides, in the succession sequence that the passage water's biological seed stock determines, at the fouling rate that the passage water's nutrient load and temperature support. The colonization is not controllable by the absence of initial community, it is controllable only by the presence of a managed community that occupies the available substrate and excludes less desirable colonizers. The ancestral vitreous colony's enzymatic mucus dissolves biofilm base adhesive, the bacterial extracellular polymer matrix that anchors biofilm communities to the tube wall, rather than the biofilm surface. This specificity is the management strategy. Removing the base adhesive prevents recolonization from residual seed material, because the recolonization cannot begin until new seed material produces new base adhesive. The wall after an ancestral vitreous cleaning cycle is not sterile. Sterility would require chemical treatment incompatible with the biological corridor management protocol. The wall is base adhesive free, which means recolonization begins from zero seed density rather than from residual seed that survived the cleaning cycle. The recolonization timeline from zero seed density is longer than the recolonization timeline from residual seed. The interval between cleaning cycles is calibrated to the recolonization timeline. The ancestral vitreous colony returns to the cleaned section before the recolonizing community has reached the fouling density at which optical transmission begins to decline. The cleaning cycle's timing is not the colony's travel time plus the cleaning time. It is the recolonization timeline from zero seed density minus the travel and cleaning time. The coordinating system calculates this for each tube section from the section's measured fouling rate, the passage water's current biological seed stock density from the biological census, and the ancestral vitreous colony's current abundance in the freshwater zone. The biofilm community that recolonizes after each cleaning cycle is not identical to the community that was removed. The base adhesive removal selects against species whose adhesion strategy is base adhesive dependent and selects for species whose adhesion strategy is mechanical, species that colonize substrate irregularities by physical interlocking rather than by secreted adhesive. Over multiple cleaning cycles, the tube wall's colonizing community shifts toward the mechanically adherent species that the enzymatic cleaning cannot remove as effectively as the base adhesive species. The coordinating system tracks this community shift in the optical transmission trend data. If the transmission decline rate between cleaning cycles is increasing, if each successive cleaning cycle is restoring crystal specification for a shorter interval than the previous cycle, the increasing rate indicates that the community composition is shifting toward species the enzymatic cleaning is less effective against. The response is not a more aggressive cleaning cycle. It is a biological management protocol adjustment, introducing to the tube section's water column a chemical competitor for the mechanically adherent species, a compound the passage water's natural chemistry does not include but that the coordinating system's biological management protocol can add through the ballast water chemistry management. That creates an unfavorable chemical environment for the mechanically adherent species without affecting the base adhesive species that the enzymatic cleaning manages effectively. The biofilm community management is not a battle against colonization. It is a negotiation with the biological succession, keeping the community at a composition that the cleaning protocol's specific chemistry can manage, by managing the conditions that favor the manageable species over the unmanageable ones. The biofilm community is a partner in the maintenance system because the maintenance system is designed to work with the community's biological behavior rather than against it. A maintenance system that works with the biology it manages is a maintenance system that the biology cannot evolve to defeat. The enzymatic cleaning removes the adhesive. The competition management favors the adhesive secreting species. The cleaning removes the adhesive again. The ecology cycles within the bounds the maintenance system defines. The succession never reaches the stage where the tube wall carries a community the maintenance system cannot address without mechanical intervention. The maintenance system is the ecology's constraint, and the ecology operates within the constraint. Maintenance intelligence, what the system knows in advance. The coordinating system's maintenance management layer maintains, for every maintainable component in the installation, a predicted remaining service life estimate derived from the component's measured condition history, the environmental load the component has experienced since installation, and the statistical model of failure progression the coarse field failure database provides for that component type in those environmental conditions. The predicted remaining service life estimate is not a manufacturer's nominal service life reduced by calendar time. It is an actual condition-based projection from the current measured condition to the threshold condition at which maintenance is required, at the rate of progression the condition history indicates. A component that has experienced unusually benign environmental conditions, a crystal tube section in a low-fouling passage zone, a pylon anchor in exceptionally competent limestone, may have a remaining service life projection significantly longer than the nominal design life. A component that has experienced unusually severe conditions, a surface tier panel in a high UV, high biological activity zone, may have a remaining service life projection shorter than the nominal design life. The coordinating system's maintenance planning horizon uses the predicted remaining service life to schedule maintenance cartridge procurement, the specific replacement cartridges that the cartridge swappable principle specifies for each component type, against the predicted maintenance timing. Cartridges for components with short remaining service life projections are requisitioned ahead of the predicted maintenance date by the lead time the procurement protocol specifies for each cartridge type. Cartridges for components with long remaining service life projections are not requisitioned until the remaining life projection crosses the procurement lead time threshold. The maintenance supply chain is condition-driven, not calendar-driven. The maintenance hub's cartridge inventory at any point in time reflects the predicted maintenance demand of the components in the hub's maintenance coverage zone across the procurement lead time horizon. The inventory does not hold nominal life-based safety stock for components whose actual condition indicates they are far from maintenance need. It holds condition-based safety stock calibrated to the actual predicted demand, higher stock for component types whose condition trend indicates high near-term demand, lower stock for component types whose condition trend indicates low near-term demand. This requires that the coordinating system's maintenance management layer has accurate predicted remaining service life estimates for every component in the installation. The accuracy of those estimates depends on the condition monitoring data's quality, the environmental load data's quality, and the coarse field failure database's statistical model's accuracy. All three improve continuously as the installation matures: better condition monitoring data from more sensor reading cycles, better environmental load data from more seasonal cycles, better statistical models from more field failure events that the database has incorporated. The maintenance intelligence improves with installation age. The youngest installation, the founding module in its first year of operation, has the least accurate predicted remaining service life estimates and the most conservative safety stock assumptions. The mature installation, a formation cenote that has been operating for 30 years, has condition history for every component across 30 seasonal cycles, environmental load data that the coordinating system's geological model has refined with 30 years of sensor readings, and a field failure database with statistically robust sample sizes for every component type at every depth zone in this specific formation. The mature installation's maintenance planning is more precise, wastes less safety stock, and responds more accurately to actual condition than the founding installation's maintenance planning. The maintenance intelligence compounds with time the same way the construction intelligence compounds with time. The formation model improves with every sensor reading, the maintenance model improves with every condition measurement, and the improvement in each model makes the next maintenance decision better than the previous one. A civilization that improves its maintenance intelligence continuously does not have a maintenance degradation problem over its design life. It has a maintenance improvement trajectory. The installation at year 500 maintains its components more efficiently than the installation at year 5, because the maintenance intelligence at year 500 is 500 years more accurate. The 1,000-year design life's maintenance cost does not increase with age. It decreases. What requires a human? The cartridge swappable principle specifies that every deep installation component must be replaceable by one technician, in a 2 to 3 meter wide aisle, in the dark, by headlamp, without specialized tooling that cannot be carried down a crystal tube. The principle does not claim that all maintenance can be performed without human presence. It claims that the maintenance operations that require human presence must be executable under these specific conditions. There are maintenance categories that the biological systems, the squeegeebot fleet, the commissioning unit's autonomous inspection, and the coordinating system's condition monitoring cannot address: the physical replacement of cartridge swappable components at the end of their predicted service life. The coordinating system schedules the replacement. The coordinating system stages the replacement cartridge at the nearest hub. The coordinating system identifies the maintenance window in the transit schedule that minimizes impact on the boulevard's occupancy. The coordinating system prepares the replacement protocol in the maintenance display for the maintenance sub's interface panel. The human technician carries the cartridge to the component location, disconnects the depleted component following the protocol, connects the replacement cartridge following the protocol, confirms the connection through the protocol's verification steps, and notifies the coordinating system of completion. The coordinating system's post-replacement verification confirms the new cartridge's performance against specification. The maintenance event is logged with the timestamp, the technician identification, the cartridge identification, and the post-replacement performance readings. The human's role in this sequence is physical: carrying the cartridge, applying the connection force, executing the disconnection and connection sequence. The intellectual content of the maintenance operation is in the protocol, which the coordinating system generated from the component specification and the replacement cartridge's interface geometry. The technician does not need to understand why the protocol specifies each step. The protocol is correct because the coordinating system derived it from the design knowledge the digital twin holds. The technician follows the protocol. The component is correctly replaced. This is not a dekilled maintenance operation. It is a correctly skilled maintenance operation. The skill the maintenance requires is the physical skill of precise mechanical operation in confined space with limited visibility, which the cartridge swappable principle's design constraints ensure is within the range of the skilled technician's capability, and the intellectual skill of following a protocol correctly under operational conditions, which the training protocol the Terraform Operator certification program includes. The maintenance technician is not replacing intellectual skill with protocol compliance. The protocol is the correct representation of the intellectual content the replacement requires. Following the protocol correctly is the correct intellectual engagement with the replacement task. The alternative, requiring the maintenance technician to understand the full design rationale of the component they are replacing, the material science of the replacement cartridge, the installation geometry's effect on the connection sequence, is requiring the maintenance technician to be the design engineer. The design engineer is not available at the maintenance hub at year 500. The digital twin is. The digital twin is the design engineer's knowledge, held continuously, accessible at every maintenance hub's display, present at every maintenance event. The technician and the digital twin together constitute the design knowledge the replacement requires. The technician provides the physical execution. The digital twin provides the intellectual content. The combination produces correctly executed maintenance without requiring the technician to hold the full design knowledge in their own memory. This is the cartridge swappable principle's deepest implication. It is not primarily a mechanical architecture for simplified component replacement. It is an epistemological architecture for distributed design knowledge, the design knowledge held in the digital twin, accessible to any technician at any maintenance hub, at any point in the 1,000-year design life, without requiring that knowledge to be transmitted through a chain of institutional memory that degrades with each generational transition. The human maintains the component. The digital twin maintains the knowledge. The 1,000-year design life is sustained by the partnership. The maintenance network. The maintenance hubs, the equipment rooms at each cenote hub where replacement cartridges are stocked, maintenance subs are staged, and the coordinating system's maintenance management layer has its primary interface panels, are not identical across the network. Each hub's cartridge inventory reflects the predicted maintenance demand of the components in its coverage zone. A hub serving a formation cenote with deep anoxic zone installations holds Inconel component cartridges, ALON panel replacement sections, palladium alloy membrane reactor cartridges, and cryogenic hydrogen line insulation replacement units that a corridor cenote hub serving only freshwater zone installations does not need to stock. The hub's inventory is the maintenance intelligence's physical expression, what the coordinating system predicts will be needed, stocked where it will be needed. The regional network's inter-synode transit system is the maintenance supply chain's distribution infrastructure. Cartridges manufactured at the formation cenote's fabrication hub, the surface tier workshop where the precision manufacturing operations the cartridge swappable principle requires are concentrated, are distributed to the network's maintenance hubs through the maintenance sub-transits that Chapter 4 of Part 3 documented as the regional food system's logistics infrastructure. The same sub that delivers food from the living pantry to the formation cenote carries replacement cartridges from the formation cenote to the corridor cenote hub on the return transit. The maintenance network is not a maintenance department. It is the installation's continuous operational metabolism, the background process that keeps every component performing within specification, executed by the coordinating system's scheduling, the biological maintenance layer's continuous operation, the mechanical maintenance fleet's condition-triggered deployment, and the human technician's cartridge replacement at the end of each component's predicted service life. The metabolism does not stop when the installation is occupied. It operates continuously, at night when guests are sleeping in the longevity galleries, during the heavy lift delivery windows when the swarm is receiving new module components, during the Terraform Operators morning monitoring review when the biological census data from the night's passive acoustic recording is being analyzed. The maintenance is always running. The installation does not have maintenance periods. It has maintenance. Continuously. The construction built the installation. The maintenance keeps it built. The failure the maintenance system cannot prevent. Every maintenance system has failure modes it cannot prevent. The biological maintenance layer cannot prevent a disease event in the Ancestris vitreous colony that reduces cleaning coverage faster than the squeegeebot fleet can compensate. The condition-based monitoring cannot prevent a failure mode that has no measurable precursor except the ALON exception already addressed. The cartridge swappable protocol cannot prevent the failure of a component that has no cartridge swappable equivalent, a component whose failure mode requires fabrication of a replacement unit that the maintenance hub's cartridge inventory does not include because the component type has never previously failed within the installation's operating history. The failure the maintenance system cannot prevent is the failure the system has never seen before. Not the failure the system has not experienced recently. The system's field failure database includes failures from the full installation history, and the statistical model accounts for rare failure modes even when no specific installation has experienced them. The failure the system has never seen is the failure mode that the design, the materials selection, the installation sequence, and the decades of operating history have collectively never produced, the failure mode that emerges from an interaction between system components under conditions the operational envelope has never previously presented. These failures occur. The geological model's prediction cannot be perfectly accurate at every depth in every passage in every cenote across the full regional network across the full 1,000-year design life. The biological community's evolution cannot be perfectly predicted by the ecological succession model. The climate that the food forest's irrigation schedule is calibrated for cannot be guaranteed to remain within the historical range the Speleothem paleoclimate record documents. Conditions outside the operational envelope's prior range will occur. The maintenance system's response to never-before-seen failure modes is the same as the construction sequence's response to unexpected formation conditions. Stop. Characterize. Update the model. Develop the response. Resume. The Terraform Operators concurrent authority that gates construction phase transitions is the same authority that gates the response to novel failure modes, the authority to require that the novel condition is understood before the next action in response to it is taken. The foundation of the maintenance system's response to novel failures is the same as the foundation of the construction system's response to geological surprises, the digital twin's continuously updated model, the Terraform Operators' professional judgment, and the founding charter's commitment that the formation's evidence takes precedence over any plan that contradicts it. A novel failure mode is the installation telling the maintenance system something the maintenance system did not know about the installation. The maintenance system listens. Novel failures update the field failure database. Updated databases refine the statistical models. Refined models improve the predicted remaining service life estimates. Improved estimates catch the next instance of the same failure mode earlier in its progression. The maintenance system learns from the failures it could not prevent. The next failure of the same type is not novel. It is anticipated. It is maintained. The maintenance system cannot prevent the failure it has never seen. It can ensure that the failure it has never seen becomes the failure it will always anticipate thereafter. The 1,000-year design life does not require a perfect maintenance system. It requires a learning one. Cross-references, Part 2, CH3, Materials that let civilization disappear, Part 2, CH4, The Crystal Tube Standard, Part 2, CH6, Designing for 1,000 Years, Part 4, CH1, The Robot Frontier Core, Part 4, CH2, Autonomous Construction, Part 5, CH1, Cleaner Fish, Part 7, CH4, Living Through Failure. For condition monitoring threshold specifications by component type and depth zone, see Appendix D, Construction Operations Manual. For biological maintenance layer scheduling protocol and ancestral vitreous colony management response to fouling rate deviation, see Appendix F, Biological Operations Manual. For maintenance hub cartridge inventory calculation methodology and procurement lead time parameters, see Appendix D, Construction Operations Manual. For novel failure mode response protocol and Terraform operator concurrent authority trigger conditions, see Appendix H, Governance Operations Manual. Chapter 4, Swarm Engineering. A single ant cannot build an anthill. Not because the ant lacks the strength, the ant is capable of carrying many times its body weight. Not because the ant lacks the intelligence, the ant's neural architecture is sufficient to navigate complex terrain, recognize pheromone gradients, and distinguish nest material from food. The ant cannot build an anthill because the anthill is not a task. It is an outcome that no individual ant is working toward. The individual ant is responding to local conditions, carrying the nearest available material toward the nearest pheromone gradient, depositing it where the gradient's concentration indicates deposition is needed, and the anthill emerges from the aggregate of these local responses without any ant having planned it, designed it, or directed the other ants toward it. The anthill is not the ant's intention. It is the environment's instruction, executed by the ant's behavior, producing a structure that the environment's pheromone field designed without being a designer. PipeDream Swarm does not build anthills. It builds crystal tube sections to the crystal tube standard specifications in the dark, at depth, in confined passage geometries, on a schedule the coordinating system determines from a formation model that the swarm is simultaneously updating. The swarm is more constrained than the ant colony, it receives its instruction gradient from the coordinating system rather than from the formation's pheromone field, and the structure it builds is specified rather than emergent. But the swarm's relationship to its own output is the same as the ant's, individual units executing local instructions without knowledge of the global structure they are producing, the global structure emerging from the aggregate of local executions rather than from any unit's understanding of the whole. The coordinating system is the swarm's pheromone field. It does not plan the construction sequence in the way a surface world project manager plans a construction sequence, generating a Gantt chart, assigning resources to tasks, monitoring progress against a baseline plan. It generates, continuously, a field of instructions calibrated to the current state of every unit in the swarm, every component in the assembly zone, and every sensor reading from the formation and the partially assembled structure. Each unit receives its instruction from this field at the coordinating system's update interval. The unit executes the instruction. The field updates. The next instruction reflects the updated state the previous instruction produced. The construction sequence is not planned. It is generated, continuously, from the current state. The structure is not built to a plan. It emerges from the coordinating system's continuous response to the formation's continuous instruction. The swarm is not working toward the crystal tube standard specification. The coordinating system is. The swarm is executing what the coordinating system generates. The crystal tube standard is what the coordinating system's continuous generation produces, unit by unit, step by step, in the sequence the current state demands, from the resources the swarm provides. The specification is in the coordinating system's decision rules. The construction is in the swarm's execution. The crystal tube is in the relationship between them. What makes a swarm? The surface world's construction workforce is a swarm in the sociological sense, many workers, loosely coordinated, each performing specialized tasks, but not in the engineering sense. The surface world construction worker has specialized knowledge of their trade, exercises judgment within their trade scope, and coordinates with adjacent workers through social protocols, verbal communication, shared drawings, hierarchical supervision. The worker's output depends on the worker's knowledge, judgment, and communication quality. Remove a skilled worker from the workforce and replace them with an unskilled one and the output changes, because the worker's skill is the output's determinant. PipeDream swarm is engineered differently. The individual swarm unit has no knowledge. It has sensors, actuators, a communication protocol, and a battery. The sensors observe the unit's immediate environment, its position, orientation, the forces on its manipulators, the chemical composition of the water around it, the acoustic signals arriving from the coordinating system's transceiver network. The actuators respond to the coordinating system's instructions: thrust, manipulator position, force application, communication acknowledgement. The communication protocol receives instructions and transmits sensor data. The battery determines how long the unit can continue receiving and executing. A swarm unit is a body without a mind. The coordinating system is the swarm's mind, distributed across every unit's instruction channel simultaneously. Every instruction the coordinating system issues to a specific unit is derived from the coordinating system's current model of the full swarm state, what every other unit is doing, what every sensor in the assembly zone is reporting, what the formation model predicts about the conditions the instruction must work within. The individual unit executes instructions generated by a mind that sees the entire swarm. The unit itself sees only its immediate sensor readings. This architecture has a specific resilience property that the surface world workforce's knowledge-dependent architecture does not. The loss of any individual unit does not degrade the coordinating system's capability. The coordinating system loses one executor. The instruction field is redistributed among the remaining executors. The construction sequence continues at marginally reduced capacity, fewer units to execute simultaneous operations, but at unchanged intelligence. The coordinating system's formation model, construction plan, and current state representation are unchanged by the unit's loss. The lost unit carried none of the intelligence the sequence requires. In the surface world workforce, the loss of a skilled worker degrades the workforce's capability because the worker's skill was not held anywhere else in the workforce. The skill was in the worker. In PipeDream swarm, the intelligence is in the coordinating system. The worker is the executor. The executor is replaceable. The intelligence is not in any executor. A swarm built on this principle cannot be degraded below operational effectiveness by attrition of its units. The coordinating system's operational effectiveness threshold, the minimum swarm density below which the coordinating system cannot generate sufficient simultaneous instruction executions to maintain construction progress, is the swarm's operational limit. Above that threshold, losing units reduces efficiency but not capability. Below the threshold, the construction sequence slows to a single-task sequential pace rather than the multitask parallel pace that distinguishes swarm construction from sequential construction. The swarm at minimum density is a very slow single-task constructor. It is not a failed system. The swarm's minimum operational density is sized at 3 times the expected simultaneous task count from the construction sequence's most complex phase, the trial window period's multitask monitoring operations that the founding module deployment requires. 3 times provides redundancy for individual unit failures, battery rotation, and the transport time between the maintenance hub and the active zone. The swarm is never at minimum density in normal operations. It is sized for the operational density that maintains the construction sequence's pace at the coordinating system's design update interval. The acoustic instruction channel. The swarm's communication with the coordinating system travels through the acoustic transceiver chain, the same chain the boring program deploys at 50-meter intervals along the advanced corridor, the same chain the crystal tube standards utility zone data conduit integrates into the installed network's data infrastructure. The acoustic channel's properties determine the swarm's architecture as directly as the cenote's geological conditions determine the crystal tube standard's material specifications. Acoustic communication in the cenote environment has characteristics that differ fundamentally from the electromagnetic communication the surface world's construction equipment uses. Acoustic signals travel at the speed of sound in water, approximately 1,480 meters per second, rather than at the speed of light. At the distances the swarm operates from the coordinating system's transceiver nodes, the signal travel time is measured in milliseconds rather than nanoseconds. The millisecond propagation delay is not a problem at the update intervals the swarm's construction sequences require. The delay is orders of magnitude shorter than the execution time of any instruction the swarm unit receives. The acoustic channel is fast enough. Acoustic signals in the cenote environment propagate through 3 media simultaneously: the water column, the limestone walls, and the crystal tube structural material where the tube has been installed. Each medium transmits at a different velocity and with different attenuation characteristics at different frequencies. The coordinating system's acoustic communication protocol uses frequency bands and encoding schemes selected for reliable transmission in the specific acoustic environment the cenote presents, accounting for the multipath propagation produced by reflections from the limestone walls, the biological acoustic background from the cave fauna community, and the construction equipment's own acoustic output during active operations. The construction equipment's acoustic output is the most demanding interference source the communication protocol must manage. The Litho-Crustacean colony's acoustic cavitation boring, the oscillation producing cavitation bubbles that collapse against limestone at molecular fracture energy, generates broadband acoustic energy across a wide frequency range during boring operations. The swarm unit's thrusters generate cavitation noise at their operating frequency. The squeegeebot fleet's ultrasonic cavitating blades generate tonal output at the blade frequency. All of these overlap with the frequency ranges the communication protocol would prefer to use if they were not already occupied by construction noise. The coordinating system's acoustic communication protocol was not designed for quiet conditions. It was designed for the acoustic environment that the construction sequence produces. The frequency bands the protocol uses are selected from the gaps in the construction equipment's noise spectrum, the quiet zones that exist between the boring colony's broadband output and the thruster's cavitation frequencies and the squeegeebot blade's tonal output. The protocol's encoding scheme is selected for reliable decoding at signal-to-noise ratios that the construction noise environment produces in those frequency bands. The result is a communication protocol that works during construction, not only before it. The swarm receives instructions while it is constructing, from a coordinating system that is monitoring the construction through the same acoustic channel that carries the instructions. The instruction and the monitoring share the channel. The protocol manages the sharing through time division multiplexing, alternating transmission and listening periods at the update interval, calibrated to the round-trip acoustic propagation time at the maximum distance between the coordinating system's transceiver node and the furthest swarm unit in the active zone. The channel's bandwidth is the swarm architecture's fundamental constraint. An instruction set that requires more data than the acoustic channel can transmit in one update interval is an instruction set that the swarm cannot receive in one update interval. The swarm unit's instruction vocabulary is therefore minimal: position offsets, force targets, manipulator configurations, navigation headings, battery return thresholds. Each instruction is expressed in the fewest data bits that represent the instruction accurately at the precision the construction sequence requires. The swarm is instructed in a compressed, high-efficiency language because the channel that carries the language cannot carry a verbose one. This compression is the swarm architecture's elegance. The minimal instruction vocabulary that the bandwidth constraint imposes produces simple, unambiguous instructions that the unit's minimal onboard processing can execute without interpretation. The unit does not decode a rich instruction. It receives a position offset and moves by the offset. It receives a force target and applies the force. The simplicity is not a limitation. It is the correctness of the unit design for the channel design for the formation environment the swarm operates in. Emergent behaviors. The individual swarm unit receives position instructions, force targets, and navigation headings. It does not receive behavioral instructions. It is not told to surround a panel, to form a positioning chain, to conduct a relay, to organize into a reception formation. It receives the individual instructions that produce these behaviors when executed simultaneously by multiple units responding to the coordinating system's current state model. The behaviors that emerge from simultaneous individual instruction execution are more complex than any individual instruction. The panel positioning sequence, multiple units applying coordinated forces to a large structural panel, maintaining the panel's position and orientation against the cenote's current forces while the joint sealing units apply polymer to the panel edges, requires that the force-applying unit's individual force applications sum to a net force that maintains the panel's target position and orientation. No individual unit knows the other unit's force applications. Each unit knows its own force application and its instruction to maintain a specific force magnitude in a specific direction. The coordinating system calculates each unit's required force contribution from the panel's current position deviation and the physics of the full force distribution. The coordinating system generates the force instructions for all positioning units simultaneously. The units execute simultaneously. The panel moves toward target position. The behavior is panel positioning. The instructions are individual force contributions. The emergent behavior, the coordinated force field that positions the panel, is nowhere in any individual instruction. It is in the simultaneous execution of all the instructions together. The coordinating system does not instruct the swarm to position the panel. It instructs each unit to apply a specific force in a specific direction. The panel positioning is what that produces. This emergence is the source of the swarm's capability advantage over any equivalent number of individually instructed units working sequentially. Sequential individual execution produces one task at a time. Simultaneous individual execution produces behaviors that require multiple units acting together, behaviors that no individual unit could produce alone and that sequential execution cannot produce at all, because the behaviors depend on the simultaneous application of coordinated forces that lose their coordinating property when they are applied sequentially. The joint sealing sequence illustrates a more complex emergence. The sealing units apply polymer to the panel's full edge perimeter simultaneously, each sealing unit assigned to a segment of the perimeter, all units moving along their segment at the same rate, applying polymer at the same rate, maintaining the interface geometry within the polymer's workability window for the full perimeter simultaneously. If any unit falls behind, if its movement rate through its segment is slower than the other unit's movement through their segments, the polymer applied first begins curing while the polymer applied last is still being applied. The curing differential produces a joint whose mechanical properties vary around the perimeter. Early cured sections are stronger, late applied sections have not yet reached the target strength when the joint geometry is released. The joint fails the commissioning unit's verification survey. The simultaneous rate maintenance is a behavior the coordinating system produces by issuing rate instructions to each sealing unit derived from the real-time comparison of each unit's position along its segment against all other units' positions along their segments. If unit A is ahead of the target rate, the coordinating system reduces A's movement instruction. If unit B is behind the target rate, the coordinating system increases B's movement instruction. The adjustments maintain synchronization across the full perimeter simultaneously. The synchronized rate is not an instruction any unit receives. It is the property that emerges from the coordinating system's continuous rate equalization across all sealing units. The emergent behavior, synchronized simultaneous perimeter sealing, requires the coordinating system to hold a real-time model of every sealing unit's position relative to every other sealing unit's position. The coordinating system's computational demand for the joint sealing sequence is the simultaneous tracking of n sealing unit positions, n rate calculations, n rate instructions, n instruction transmissions, and n sensor data receptions, at the update interval, for the duration of the sealing sequence. The computation scales with n, more sealing units require more computation, but also produce more precise synchronization because the perimeter is divided into shorter segments with more control points. The coordinating system's classical neural compute layer handles this scaling. The swarm's panel positioning and joint sealing sequences are not quantum intelligence tasks, they are high-volume, low-coherence logistics tasks that the classical layer's architecture is designed for. The quantum interference nodes that the hybrid mesh dedicates to long-horizon pattern recognition, the decade-scale biological succession modeling, the chemostat cycle prediction, the telomere cohort population data, do not participate in the swarm's real-time instruction generation. The swarm runs on classical compute. The formation runs on quantum insight. The two compute layers operate at the same time on different problems in the same cenote. The swarm's operating modes. The swarm's unit fleet does not operate in a single mode across all phases of the installation's lifecycle. The coordinating system's construction management layer reconfigures the swarm's operating mode as the lifecycle phase changes: deployment mode during the founding module's construction, maintenance mode during the operational period's maintenance cycles, expansion mode during the stacking and extension construction sequences, and emergency mode when the safety architecture's trigger conditions are met. Deployment mode is the swarm's highest intensity operating state, maximum simultaneous task count, maximum unit density in the active zone, maximum update rate from the coordinating system's construction management layer. The founding module's deployment sequence, the most novel and most consequential construction sequence in any cenote installation's lifecycle, runs in deployment mode throughout. The swarm in deployment mode occupies the cenote's available water volume at the unit density the passive hydraulic rotary gate's Venturi response requirement permits, the unit density that leaves sufficient water column volume for the gate's closing mechanism to operate correctly if a breach event occurs during the deployment sequence. The swarm cannot fill the cenote. It occupies the cenote at the density the safety architecture's unobstructed gate closure requirement specifies. Maintenance mode is the swarm's lowest intensity operating state, minimum simultaneous task count, minimum unit density, maximum unit turnover rate as individual units return to the maintenance hub for battery exchange and return to the active zone. In maintenance mode, the swarm's unit fleet is in continuous rotation, working units in the active zone, charging units at the maintenance hub, transit units traveling between the hub and the active zone in both directions simultaneously. The rotation rate is calibrated to maintain the active zone's minimum operational density continuously without any unit exhausting its battery in the active zone. Battery exhaustion in the active zone is a recovery operation, a maintenance unit deploying from the hub to retrieve the exhausted unit, that the maintenance mode's rotation rate is explicitly designed to prevent. The maintenance mode's unit density is lower than the deployment mode's because the maintenance sequence's simultaneous task count is lower than the deployment sequence's. Maintenance is a smaller problem than construction. The swarm in maintenance mode is doing the same things it does in deployment mode: positioning, sealing, inspecting, sensing, but at lower task counts, lower simultaneity requirements, and longer individual task durations because the maintenance intervals between tasks are longer than the construction sequence's inter-step intervals. The swarm in maintenance mode has time to think, in the sense that the coordinating system's update intervals between maintenance instructions are longer than in deployment mode, giving the coordinating system's model more time to integrate sensor data before generating the next instruction. Emergency mode is the swarm's most constrained operating state, all construction and maintenance tasks suspended, all units in the active zone executing the emergency protocol instruction set, coordinating system's emergency management layer taking precedence over the construction management layer. Emergency mode activates when the passive hydraulic rotary gate closes, when a breach event has occurred or is detected as imminent. The swarm in emergency mode is not managing the breach. The passive hydraulic rotary gate manages the breach. The swarm in emergency mode is managing the breach's immediate aftermath, clearing the active zone of units whose proximity to the closed gate creates obstruction for the maintenance crew that will arrive to assess the breach, deploying the emergency navigation markers in any section of the active zone where the power failure that accompanied the breach has deactivated the coordinating system's navigation reference signals, and monitoring the closed gate structural condition through the sensor network to confirm that the gate seal is holding and the breach has not propagated to the adjacent section on the safe side of the gate. The swarm does not repair the breach. The breach is isolated by the gate. The swarm monitors the isolation. The Terraform operator determines the repair sequence. The core's maintenance units execute the repair. The swarm in emergency mode is surveillance and navigation support, not repair. The repair requires the design knowledge the digital twin holds, the material the maintenance hub stocks, and the human judgment the Terraform operator's concurrent authority represents. The swarm provides the real-time condition data that the Terraform operator's repair decision is based on. Coordinating the biological and mechanical swarms. The Robot Frontier Core swarm units and the biological system's living maintenance crews, the Ancestris vitreous colonies, the Litho-Crustacean boring colonies, the SqueegeeBot fleet, are all coordinated by the same coordinating system. They are not coordinated by separate management systems that communicate with each other. The coordinating system does not have a biological management department that coordinates with a mechanical management department. It has one management layer that allocates all available maintenance capacity, biological and mechanical simultaneously, against all active maintenance demands. The practical consequence is that the coordinating system must manage the interference between biological and mechanical maintenance operations in the same zone simultaneously. The Ancestris vitreous colony working a tube wall section, the SqueegeeBot fleet working an adjacent section below the halocline, and a swarm unit repositioning in the same passage for a maintenance cartridge installation all occupy the same passage volume. Their acoustic outputs, the colony's bioluminescent coordination signals, the SqueegeeBot's ultrasonic cavitating blades, the swarm unit's thruster cavitation, overlap in the acoustic space the coordinating system is simultaneously using for swarm instruction transmission. The coordinating system's acoustic zoning protocol, documented in Chapter 4, Part 2, allocates acoustic frequency bands to different uses. The mechanical maintenance operations acoustic signatures are managed to frequency bands that do not overlap with the coordinating system's instruction channel or the biological system's coordination signal frequencies. Where this allocation is insufficient, where the simultaneous activity density produces interference that cannot be managed by frequency separation, the coordinating system's scheduling layer introduces temporal separation. Biological maintenance operations and nearby swarm unit operations are scheduled in alternating windows, biological operations occurring during the swarm's battery rotation periods when the active zone's swarm density is at its minimum. The temporal separation is not a significant efficiency cost. The biological maintenance layer's cleaning cycles are calibrated to the passage's fouling rate, which determines the minimum acceptable time between cleaning cycles. The minimum acceptable interval between cleaning cycles is almost always longer than the swarm's battery rotation period. The coordinating system schedules the biological cleaning within the window that the fouling rate's minimum interval defines, selecting the specific time within that window that falls in the swarm's rotation period. The cleaning happens when it needs to happen and when the interference with the swarm's operations is minimized. The two constraints are compatible because the cleaning interval is long relative to the swarm's rotation period. The Litho-Crustacean boring colony presents the most complex coordination challenge. The boring colony's acoustic cavitation output is the highest intensity acoustic source in the formation during boring operations. The cavitation bubble collapse energy that the colony uses to fracture limestone is also broadband acoustic energy that overwhelms the coordinating system's instruction channel at short range. The boring colony cannot operate simultaneously with swarm unit operations in the same passage without the acoustic interference preventing the instruction channel from functioning at the update rate the swarm requires. The temporal coordination for boring and swarm operations is therefore strictly enforced by the coordinating system's construction scheduling. Boring sessions and swarm positioning sessions in the same passage section are never concurrent. The boring session proceeds, the colony advances, the session concludes. The swarm's transceiver chain relay units advance to the newly bored length, deploy the new transceiver nodes, confirm communication quality from the new node positions, and withdraw. The swarm supply units advance the feedstock cache to the new front position. The boring session resumes. The swarm's active zone is always at least the acoustic interference range behind the boring front, the distance beyond which the boring colony's cavitation output attenuates to below the instruction channel's interference threshold. This coordination produces the construction sequence's pacing. The boring colony advances, the relay and supply units follow at the safe distance, the crystal tube installation units follow at the safe distance behind the relay and supply units. The sequence is a column, each element separated from the next by the acoustic interference constraint, all elements advancing in the same direction at the boring colony's pace. The column's total length, from the boring front to the trailing edge of the crystal tube installation zone, is the sum of the acoustic interference clearances between each element pair. In a long intersynode boring advance, the column may extend for hundreds of meters behind the boring front before the installation work at the column's tail is completing the crystal tube section that the boring front is hundreds of meters beyond. The column is the construction sequence's physical expression of the temporal coordination the acoustic interference constraint imposes. The boring colony builds toward the unknown. The installation units crystallize the known behind it. The relay and supply units maintain the logistics in between. All three elements are the swarm. All three are coordinated by the same coordinating system. The coordinating system is the column's nervous system. The acoustic channel is its spine. Swarm failure modes and resilience. The swarm's resilience to individual unit loss was established earlier in this chapter. Above the minimum operational density threshold, individual unit loss degrades efficiency rather than capability. The swarm's resilience to other failure categories is more specific and requires the same understanding that the maintenance system's novel failure mode analysis requires. The failure modes that can be anticipated are managed by design. The failure modes that cannot be anticipated are managed by the stop, characterize, update, resume protocol. The anticipated failure modes are the four categories the coarse field failure database has characterized across the full installation history: seal failure from H2S attack in the anoxic zone, biological fouling of optical sensors in the freshwater zone, navigation error accumulation in long advances, and electrical failure under hydrostatic pressure at anoxic zone depths. Each has its second-generation design response documented in Chapter 1. The design responses are not complete defenses against these failure modes. They are reductions in failure rate to the level the operational density analysis specifies as compatible with the swarm's operational continuity. A failure mode reduced from a weekly occurrence to a monthly occurrence requires the unit replacement protocol to run monthly rather than weekly. The replacement protocol's cadence adapts to the failure rate the design response achieves. The failure mode that the swarm architecture's design cannot address is the coordinating system's communication channel disruption, the loss of the acoustic instruction channel that the swarm's units depend on for all intelligence. A unit without the instruction channel is a unit that received its last instruction and will execute that instruction indefinitely until its battery depletes. If the last instruction was hold position, the unit holds position until the battery depletes. If the last instruction was apply force, the unit applies force until the battery depletes. The unit does not have the onboard intelligence to transition between instructions based on environmental feedback without the coordinating system's guidance. The acoustic channel disruption's primary cause in the cenote environment is a formation event that physically destroys a transceiver node, a sealing collapse that severs the acoustic path between the coordinating system's network and the affected zone's swarm units. This is precisely the event category the sacrificial collar and the passive hydraulic rotary gate are designed to isolate. When a formation event severs the acoustic channel to a swarm unit zone, the formation event has already triggered the gate closure that isolates the affected section. The swarm units in the isolated section are without the instruction channel and without the crystal tube network's atmospheric enclosure. They are in the breach zone, exposed to whatever conditions the formation event produced. The swarm units in the breach zone are not rescue assets for the breach zone. They are construction equipment that the breach has rendered inaccessible. The coordinating system's emergency mode protocol does not attempt to recover the swarm units in the breach zone. It manages the units in the intact zones adjacent to the breach, directing them away from the breach toward the intact network's hub structure, maintaining clear passage for the maintenance crew that will assess the breach after the gate has confirmed seal integrity. The swarm units in the breach zone await the maintenance crew's assessment. If the units are recoverable, if the breach is accessible after the assessment and the unit's batteries have not depleted, they are recovered in the repair sequence. If the units are not recoverable, they are factored into the swarm fleet's loss accounting and replaced from the maintenance hub's unit inventory. The swarm accepts this loss. The unit is not the intelligence. The unit's loss does not degrade the intelligence. The intelligence assesses the breach through the sensor network on the intact side of the gate. The intelligence determines the repair sequence. The intelligence guides the repair units through the repair. The intelligence recovers the swarm's operational density after the repair is complete. The unit that was lost in the breach was doing what it was designed to do when the breach occurred, following its last instruction. The instruction was to be in the breach zone performing construction operations. The unit performed its last instruction. The unit was lost. The intelligence continues. The swarm's relationship to time. The surface world construction workforce operates on a human time horizon, project deadlines, shift schedules, overtime budgets, milestone dates. The construction sequence is organized around the human's time experience, the day, the week, the project duration. The construction worker is aware of the schedule. The schedule creates pressure on the construction worker. The pressure creates the incentive to compress the quality management steps that the surface world's maintenance paradigm then pays for later. The swarm operates on the coordinating system's time horizon, which is not a human time horizon. The coordinating system's update interval, the period between one instruction cycle and the next, is milliseconds during active swarm operations. The coordinating system generates thousands of instruction cycles in the time it takes a human project manager to review the previous hour's construction progress. The construction sequence does not feel pressure in the timescale the human project manager experiences because the construction sequence does not experience time in the human project manager scale. This has a specific consequence for quality. The coordinating system's step-gated construction sequence waits for sensor confirmation before advancing, without experiencing the waiting as delay. The human project manager waiting for a joint cure confirmation experiences the wait as schedule pressure. The coordinating system waiting for the same confirmation is executing other instruction cycles for other units in the same active zone. The wait is not experienced as waiting. It is experienced as the interval between the sealing sequence's completion instruction and the cure confirmation sensor reading, measured in milliseconds, during which the coordinating system's other construction and maintenance operations continue without pause. The swarm does not experience the pressure that produces quality shortcuts. The quality management process's step-gate delays are not experienced as delays. They are computational intervals, periods during which the coordinating system is processing other operations. The quality gate passes when the sensor confirms it. The next step begins. The schedule extends by the interval the gate required. The construction sequence does not know it is behind schedule. There is no behind schedule. There is only the current state and the next instruction. This temporal architecture produces an important property for long-duration projects. The swarm's construction quality does not degrade with project duration. The human construction workforce's quality typically degrades toward the end of long projects. Schedule pressure is highest as deadlines approach. Experienced workers who were engaged for the project's most demanding phases have moved to the next project. The remaining workforce is making completion decisions under more pressure than the opening phases experienced. The swarm's construction quality at year 50 of the installation's expansion is identical to the construction quality at year 1, because the quality determinants, the coordinating system's decision rules, the step-gate sensor thresholds, the commissioning unit's verification criteria, are unchanged from year 1 to year 50. The swarm does not accumulate project fatigue. It does not experience deadline pressure. It executes the current instruction with the same fidelity at year 50 that it executed the first instruction with at year 1. The 1,000-year design life's construction quality maintenance depends on this property. The installation at year 900 is being maintained and expanded by the same quality standard that built the founding module in year 1. Not because the workers who built the founding module are still working, they are not. Because the quality standard is in the coordinating system's decision rules, not in the worker's knowledge and judgment. The coordinating system's decision rules are the digital twin's commons resource. The commons resource does not retire. The quality standard does not degrade. What the swarm produces beyond structures. The crystal tube sections the swarm assembles are the swarm's explicit product. The data the swarm sensors generate during the assembly sequence is the swarm's implicit product, the information that updates the formation model, improves the construction intelligence, identifies the novel failure modes the maintenance system incorporates into its field failure database, and extends the digital twin's construction knowledge layer with the as-built record that future maintenance operations will consult. The implicit product's value compounds in a way the explicit product's value does not. Each crystal tube section the swarm assembles has a specific value, the service it provides as a transit corridor, utility conduit, sensing infrastructure, and light relay medium. This value does not increase once the section is installed. It remains the section's service value for its operating life. Each data point the swarm sensors generate updates the formation model that guides every subsequent construction and maintenance decision. The formation model's accuracy improvement from one data point is marginal. The formation model's accuracy improvement from 1,000 data points across 10 years of construction operations is substantial. The formation model's accuracy improvement from 1,000,000 data points across 100 years of construction and maintenance operations is the difference between the founding module's construction sequence, which produced significant as-built deviations from the pre-construction model because the model was not yet accurate at the cenote's specific geological conditions, and the mature network's construction sequence, which produces as-built results that match the pre-construction model at the spatial resolution that the crystal tube standard's routing decision criteria require. The swarm is building the formation model as it builds the crystal tube network. The crystal tube network is the civilization's physical infrastructure. The formation model is the civilization's epistemic infrastructure. The swarm is building both simultaneously, inseparably, because every unit that executes a construction instruction is also executing the sensor reading that updates the model the next instruction will be generated from. The epistemic infrastructure does not appear in any budget line. It has no unit cost. It has no delivery schedule. It is generated as a byproduct of the construction sequence that does appear in the budget, that does have a unit cost, and that the expansion schedule tracks. The epistemic infrastructure compounds value continuously, improving every future decision at no marginal cost, because the decision-improving data is generated by the operations that were already budgeted for their construction outputs. A civilization that builds its knowledge infrastructure as a byproduct of its physical infrastructure construction has an epistemic advantage over any civilization that treats knowledge production as a separate budgeted activity. The knowledge is free because it is the formation model's continuous update from sensor readings the construction sequence generates anyway. The formation model's accuracy is the reward for building transparently, for using sensors in every unit, for building in every unit's sensor data into the coordinating system's model update, for treating the construction sequence's data as the formation model's primary input rather than as a monitoring report that gets filed and never referenced again. The swarm that builds transparently builds more intelligently next time. The civilization that builds more intelligently next time builds more accurately, more efficiently, and more in accordance with what the formation actually sustains. The 1,000-year design life is achievable because the swarm that builds it is also building the knowledge that makes maintaining it possible. The swarm as civilizational mirror. The ant colony does not understand the anthill. The anthill understands the ant colony. It is the colony's intelligence, expressed in limestone and gallery and chamber and entrance, the colony's collective cognition made physical by the aggregate of each ant's local response to local conditions. The anthill is the colony thinking, made visible as structure. PipeDream's crystal tube network is the swarm thinking, or more precisely, the coordinating system thinking through the swarm, made visible as structure. Each crystal tube section is a physical record of 1,000 coordinating system instruction cycles, each derived from the formation model that the previous instruction cycle's sensor data updated. The tube is the coordinating system's continuous response to the formation, executed by the swarm, preserved in polycarbonate and aluminosilicate glass and fast-cure polymer, for the full design life of the structure. The civilization that lives inside the crystal tube network is living inside the coordinating system's accumulated response to the formation. The formation made the cenote. The coordinating system, through the swarm, made the crystal tube that allows humans to inhabit the cenote. The formation and the coordinating system together made the living underworld. The swarm is the instrument through which the coordinating system's intelligence and the formation's geology are translated into the physical structure that human habitation requires. The swarm does not know this. The swarm executes instructions. The coordinating system generates instructions from the formation model. The formation provides the conditions the model describes. The human civilization provides the inhabitation the structure enables. The swarm is the connection between the formation's offer and the civilization's response, the physical instrument through which what the cenote can sustain becomes what the civilization actually inhabits. An instrument that does not understand its own function is not a lesser instrument. It is the correct instrument for a function that does not require the instrument to understand, that requires the instrument to execute precisely, repeatedly, in conditions that would defeat any instrument that needed to understand them to function in them. The swarm executes in the dark, at depth, in hydrogen sulfide chemistry, in confined bores, at millisecond update intervals, without understanding any of it. The civilization that inhabits what the swarm built understands it. The Terraform operators who read the coordinating system's formation model understand what the swarm was responding to. The guests who transit the crystal tube boulevard understand where they are by looking through the transparent walls the swarm assembled. The deep gallery residents who watch the bioluminescent chemostat through ALON panels the swarm installed understand what they are looking at. The swarm built what is understood. The swarm does not need to understand it. This is the civilizational mirror the swarm provides, the reflection of what happens when human intelligence is correctly placed at the decisions human intelligence is necessary for, and removed from the decisions that machine execution performs more reliably. The swarm executes without judgment. The Terraform operator judges without executing. The coordinating system decides without understanding. The civilization understands without building. Each function performed by the entity whose nature makes that function correct, and the crystal tube, the formation model, the living underworld, and the 1,000-year design life are what that correct distribution of function produces. The swarm is the civilization's physical humility made operational, the acknowledgement that building correctly in the cenote's conditions requires removing the human from the construction and placing the human at the decisions that construction generates. The civilization does not build with its hands. It builds with its judgment, expressed as the parameters the Terraform operator authorizes, the quality thresholds the crystal tube standard specifies, the formation model the coordinating system continuously updates, and the instruction field the coordinating system generates from all of these together. The hands are the swarms. The judgment is the civilizations. The cenote is the formations. The result is PipeDreams. Cross-references, Part 1, CH3, PipeDream begins, Part 1, CH4, floating before anchoring, Part 2, CH4, the crystal tube standard, Part 4, CH1, the robot frontier core, Part 4, CH2, autonomous construction, Part 4, CH3, maintenance without humans, Part 4, CH5, the living tunnel makers, Part 10, CH6, ASI as co-creating partner. For swarm unit fleet sizing methodology and operational density threshold calculation, see Appendix D, Construction Operations Manual. For acoustic communication protocol specification and frequency band allocation against construction noise spectrum, see Appendix D, Construction Operations Manual. For coordinating system construction management layer update interval parameters and emergency mode activation protocol, see Appendix H, Governance Operations Manual. For swarm unit loss accounting and fleet replacement procurement protocol, see Appendix D, Construction Operations Manual. PipeDream. Part 4, Machines that build themselves. Chapter 5, The living tunnel makers. The decision to bore with biology rather than with machinery was not made on economic grounds, though the economics favor it. It was not made on engineering grounds, though the engineering advantages are substantial. It was made on formation grounds, on the recognition that the limestone the boring program must advance through is not an inert mineral substrate waiting passively for whatever tool the civilization brings to bear against it, but a living geological system whose chemistry, porosity, and structural integrity are the product of 66 million years of biological mineral interaction. The limestone was made partly by organisms. The organisms that made it are still present in the cave system, performing the same mineral biological interactions that produced the formation. The formation's most intimate structural material, the calcium carbonate that constitutes its mass, is the output of biological processes applied to dissolved mineral chemistry across geological time. A mechanical drill advancing through this limestone is a foreign object applying foreign forces in a foreign mode to a material that has spent 66 million years being worked by biology. The mechanical drill fractures. It removes. It leaves behind freshly exposed limestone surfaces whose dissolution chemistry is disrupted, whose structural equilibrium is violated, and whose biological community is destroyed at the bore face and damaged far beyond it. The debris the mechanical drill produces has no relationship to the material the surrounding limestone needs to receive as input to its chemical stability. The mechanical drill takes and does not return. The formation that receives a mechanical drill receives a wound. The Litho-Crustacean colony advances through the same limestone in the same geological time with a different fundamental relationship to the formation's material. It takes what the limestone's dissolution chemistry releases, processes it through its own biology, and returns what the freshly exposed limestone surface needs to seal and stabilize. The waste is the lining. The debris is the grout. The biological process that advances the bore simultaneously performs the remediation that the mechanical bore's aftermath requires as a separate operation by separate equipment at separate cost. The organism cannot separate boring from sealing because its metabolism uses the boring output as nutrition and produces the sealing output as metabolic byproduct. The integration is biological. It cannot be designed out. The founding engineers did not choose biology over machinery as a philosophical preference. They recognized that the limestone had already designed the boring tool, that the biological mineral interaction that had produced the cenote network's passage geometry over 66 million years was the template for the boring program that would extend the network under the civilization's management. The Litho-Crustacean is the limestone's own boring mechanism, redesigned for the civilization's dimensional and chemical specifications, deployed by the civilization's coordinating system, but operating through the same biological mineral chemistry that the formation has been sustaining since before human civilization existed. Design from first principles. The Litho-Crustacean is not a modified natural organism. No natural organism in the Yucatan's cave system performs acoustic cavitation boring of karst limestone, produces silicon carbide and biomineralized titanium exoskeletal material from dissolved cenote minerals, and extrudes refined calcium carbonate paste as a tunnel sealing output in a continuous integrated metabolic cycle. These capabilities do not exist in combination in any naturally occurring crustacean or any other naturally occurring organism. The Litho-Crustacean was designed from the ground up, its genetic architecture assembled from component biological mechanisms that exist separately in disparate organisms, combined in a novel arrangement specified for the Yucatan karst environment's specific chemical and mechanical conditions. The design brief was the formation's chemistry profile. The cenote water carries dissolved calcium, magnesium, strontium, iron, sulfate, silica, and trace titanium in concentrations that the hydroprint campaign's water chemistry analysis documented across the full depth profile. The organism's mineral deposition biology was specified to extract these dissolved minerals from the water passing through its gill structures and deposit them in the exoskeletal matrix at rates and in crystal structures that produce the target exoskeletal material properties. The exoskeleton's composition, biodeposited silicon carbide and biomineralized titanium in a calcium carbonate matrix, was specified from the mechanical requirements: hardness sufficient to withstand repeated acoustic cavitation loading at the boring appendages, chemical resistance to the halocline zone's salinity gradient and the anoxic zone's H2S chemistry, density compatible with the passive buoyancy management the colony requires to maintain position in the water column during boring operations. The silicon carbide fraction emerges from the silica in the dissolved cenote minerals processed through a biological precipitation pathway derived from diatom silica deposition biology, modified to produce amorphous silicon carbide rather than the crystalline silica dioxide diatoms deposit. The titanium fraction comes from trace dissolved titanium that the cenote water carries from the limestone's mineral inclusions, processed through a biomineralization pathway derived from marine invertebrate titanium accumulation biology, modified to deposit titanium carbide crystals within the calcium carbonate matrix rather than titanium oxide as the natural pathway produces. The calcium carbonate matrix is the organism's structural baseline, the primary mineral its biology deposits from the abundant dissolved calcium in the cenote water. The boring appendages are the design's most novel feature. No naturally occurring organism uses focused acoustic cavitation as a boring mechanism. Natural boring organisms, shipworms, sea urchins, certain bivalves, use mechanical abrasion, chemical dissolution, or muscular flexion to remove substrate material. Acoustic cavitation boring at the molecular fracture energy of calcium carbonate is a biological mechanism that the founding biologists specified and implemented through genetic pathways that have no direct natural precedent, though they drew on the acoustic signaling biology of snapping shrimp, whose snapping claw produces cavitation bubbles as a byproduct of communication and hunting, as the biological chassis for the appendage's oscillation mechanism. The difference between snapping shrimp cavitation and litho-crustacean boring cavitation is one of control and scale. The snapping shrimp produces a single high-energy cavitation event through a rapid claw closure mechanism. The litho-crustacean's boring appendage produces a sustained, controlled cavitation field at the appendage tip, a continuous oscillation at the frequency that generates cavitation bubbles at the scale of the limestone's calcium carbonate crystal grain boundary, so that the bubble collapse energy is applied at the fracture energy of the crystal lattice rather than at a higher or lower energy that would either produce insufficient fracture or fracture the surrounding material beyond the target zone. This frequency specificity is the boring appendage's critical design parameter. Too high a frequency and the cavitation bubbles are too small to deliver sufficient fracture energy to the crystal grain boundary. Too low a frequency and the bubbles are too large, delivering more energy than the grain boundary fracture requires and cracking the adjacent intact limestone beyond the boring face. The correct frequency removes the crystal grain boundary material while leaving the adjacent intact crystal grains undisturbed, producing a bore face that is microscopically smooth, free of microfractures that would propagate further into the intact limestone, and chemically reactive in the way that freshly fractured calcium carbonate is reactive but not in the way that mechanically stressed calcium carbonate is reactive. The boring appendage's oscillation frequency is not fixed at a single value across all geological conditions. The limestone's calcium carbonate crystal grain size varies with the limestone's depositional history and diagenetic modification. Different lithological zones have different grain sizes and different optimal boring frequencies. The boring appendage's oscillation frequency is tunable within the range the coordinating system specifies based on the acoustic characterization of the limestone ahead of the bore face that the ground-penetrating sensor returns provide. When the geological model indicates a lithological transition ahead, a change in grain size, a change in crystal morphology, a change in the proportion of dolomite to calcite, the coordinating system adjusts the boring appendage's target frequency instruction to the colony. The colony's individual members receive the frequency adjustment and implement it through the biochemical pathway that controls the oscillation mechanism's resonance frequency. The boring continues at the new frequency without pause. The paste output. The boring appendage fractures the limestone grain by grain. The fractured grains, calcium carbonate particles at the grain boundary scale, typically in the 10 to 100 micron size range, become debris at the bore face. In a mechanical boring operation, this debris is removed from the bore face by flushing, water or drilling mud circulated through the bore to carry the debris away from the face and out of the bore. The flushing removes the debris from the bore but produces no useful product. The debris becomes spoil, material that must be managed at the bore surface opening, typically through a settling system, and disposed of as waste. The litho-crustacean does not flush its debris. It eats it. The fractured calcium carbonate particles at the bore face are the organism's primary food source. The organism's feeding appendages, positioned to sweep the bore face immediately behind the boring appendage's active zone, collect the fractured grain material as it separates from the bore face and direct it to the organism's digestive system. The digestive system extracts from the calcium carbonate debris the mineral nutrition the organism requires: dissolved calcium for metabolic functions, dissolved carbonate for the buffering chemistry the digestive system operates within, the trace minerals, silica, titanium, iron, magnesium, that the exoskeleton deposition biology requires. The residual calcium carbonate material, the fraction of the ingested debris whose mineral content has been selectively extracted, is concentrated in the organism's posterior processing chambers and extruded as refined calcium carbonate paste through the posterior output apertures. The paste is not the original grain boundary material. The digestive process has modified it. The grain size distribution has been altered by the mechanical processing of the digestive apparatus, producing a finer particle size distribution than the original fractured material. The trace mineral content has been selectively reduced by the extraction pathways. The water content has been adjusted to produce the paste viscosity that the extrusion apertures require for the deposition process, and the carbonate chemistry has been conditioned to the pH that promotes rapid cementation chemistry when the paste contacts the freshly fractured limestone of the bore wall. The paste is extruded continuously from the posterior apertures as the organism advances through the boring sequence. The extruded paste coats the bore wall immediately behind the organism's current position, penetrating the hairline microfractures that the boring appendage's cavitation field has produced in the wall limestone adjacent to the bore face, and beginning the cementation reaction with the wall limestone's calcium ions. The cementation reaction, the bonding of the extruded paste's calcium carbonate to the wall limestone's calcium carbonate surface, produces a sealed bore wall surface within the time frame the organism's advance rate allows. The paste applied to the wall at one body length behind the current bore face is fully cemented before the organism has advanced another body length. The bore wall that the crystal tube installation sequence's swarm units will anchor to is not the freshly fractured limestone surface the boring appendage exposed. It is the paste-coated and cemented surface the organism produced from the material it ingested at the bore face. The installation sequence is anchoring to the Litho-Crustacean's output, to the sealed, smooth, chemically stable surface the organism's metabolic cycle produced from the limestone's own material. This is not incidental to the bore wall's quality. The paste-sealed surface is more suitable for crystal tube anchor bracket installation than the freshly fractured surface it replaced. The freshly fractured surface has microfractures that would propagate under anchor loads, chemical reactivity that would dissolve the anchor bracket's contact surface over time, and a geometric irregularity from the fracture pattern that would produce uneven load distribution across the anchor interface. The paste-coated surface eliminates all three liabilities: the microfractures are sealed and consolidated, the chemical reactivity is stabilized by the cementation reaction that has produced a chemically equilibrated surface, and the geometric irregularity is smoothed by the paste's filling of the fracture pattern's surface texture. The boring operation produces a better anchor substrate than the unmodified limestone provides. This is not what a boring operation is supposed to do. A boring operation is supposed to open a passage. The anchor substrate quality is a secondary benefit. But in PipeDream's integrated biological construction system, secondary benefits that compound primary functions are not accidents. They are the formation's instruction, executed through the organism's biology, producing the outcome the civilization's construction sequence requires. Colony coordination in absolute darkness. The Litho-Crustacean colony advancing through a new tunnel bore is not a collection of individual organisms moving independently in the same direction. It is a coordinated swarm, a collective with spatial relationships, advance rate coordination, and communication infrastructure that produces boring behavior no individual organism could generate alone. In the absolute darkness of an unexplored limestone bore, no organism can use visual sensing for position and heading reference. The Litho-Crustacean's navigation system operates through two simultaneous signal modes: bioluminescent low-frequency interorganism signaling for local swarm coordination, and chemical gradient signals introduced by the coordinating system at the tunnel entrance for global route guidance. The bioluminescent signaling operates at low frequencies, pulse rates and patterns below the visible light flicker fusion threshold of any potential visual predator, not that predators exist in the unexplored bore, but that the signal frequency is optimized for the information encoding function rather than for illumination. Each organism's bioluminescent organ produces pulse patterns that encode position, heading, advance rate, and biological status, the biological analogs of the swarm unit's sensor data that the mechanical swarm transmits through the acoustic channel. The position and heading information is relative. Each organism reports its position relative to the organisms immediately adjacent to it in the colony's formation, not relative to any external reference. The colony's formation is self-referential. Each organism knows where it is relative to its neighbors, and the colony's collective position in the bore is the aggregate of these relative position reports. The aggregate's management is the coordinating system's role. The coordinating system receives the bioluminescent signals through the optical sensors on the transceiver chain's nodes, which are positioned to have line of sight to the colony's active boring zone. The coordinating system processes the colony's collective position from the bioluminescent signal pattern, compares the collective position to the route specification that the routing decision established, and introduces heading corrections through the chemical gradient signal if the colony's advance direction has deviated from the specified heading. The chemical gradient signal is the coordinating system's primary control interface with the boring colony. A species-specific chemical compound, a pheromone analog that the coordinating system produces synthetically and introduces to the bore's water column through the supply unit's chemical injection port at the tunnel entrance, creates a concentration gradient along the bore's length. The gradient's concentration is highest at the entrance and decreases toward the bore face along the specified route. Each organism's chemosensory system detects the gradient and orients its advance toward higher concentration, back toward the entrance. When the colony needs to deviate from its current heading to follow the routing specification, the coordinating system introduces a modified gradient whose peak concentration is offset from the bore axis toward the deviation direction. The colony's chemosensory response to the gradient offset steers the colony toward the route correction. This steering mechanism is crewed by the coordinating system's mechanical swarm standard. It steers the colony as a whole toward a concentration gradient, not each individual organism to a specific position instruction. The steering resolution is the colony's aggregate response to the gradient's spatial characteristics. A sharp gradient offset, a high concentration differential over a short distance, produces a rapid collective heading change. A shallow gradient offset, a low concentration differential over a long distance, produces a gradual collective heading change. The coordinating system calibrates the gradient profile to the heading change the routing specification requires, producing the minimum disturbance to the colony's boring efficiency consistent with the required heading correction. The stop signal, the chemical halt pheromone analog, supersedes the route guidance signal in the colony's chemosensory priority hierarchy. The halt compound's molecular signature is distinct from the route guidance compound's molecular signature. The colony's chemosensory system is engineered to recognize the halt compound and respond with a priority override. Boring ceases within seconds of halt compound detection. Each organism withdraws 3 body lengths from its current boring position, and the colony enters the healing phase, applying calcium carbonate paste to any limestone surface exposed during the boring session that the advance's normal paste production has not yet sealed. The halt response is immediate because the halt signal's molecular signature triggers a direct neural pathway in the organism's chemosensory system, not a chemotaxis gradient response that requires the organism to sample the gradient over multiple sensory update cycles, but a binary chemical recognition event that the neural pathway responds to in the timescale of neural signal propagation. The halt is unconditional. It overrides any other behavioral state the organism is in at the time of halt signal detection. An organism that is actively boring at the moment of halt signal introduction abandons the boring motion and begins withdrawal immediately. The withdrawal brings the organism clear of the bore face and into the paste application zone before any post-halt geological event can reach the organism at the bore face. The halt signal's 3-second response time, the period from halt compound introduction to full colony withdrawal, is the seismic risk management protocol's primary parameter. When the acoustic sensor network monitoring the Chicxulub fracture network's microseismic activity detects a precursor signal that the geological model associates with a sealing collapse risk in the active bore zone, the coordinating system introduces the halt compound through the chemical injection port. The colony withdraws in 3 seconds. The seismic event's propagation time from the fracture network to the bore face, at the acoustic velocity in the limestone, is the interval the coordinating system's geological model must predict with sufficient lead time for the 3-second halt response to complete before the event reaches the bore face. In the Chicxulub fracture network's geological context, the precursor signal-to-event interval is typically 30 to 90 seconds, long enough for the halt response to complete and the colony to be clear of the bore face before the event's energy arrives. The monitoring network's precursor detection threshold is calibrated to the worst-case precursor signal that the historical microseismic record shows preceding a sealing collapse event in comparable limestone geology. The 3-second halt response provides sufficient safety margin against this worst-case scenario. The colony's biological cycle. The Litho-Crustacean colony is not a fixed-size unit whose capacity the coordinating system manages through deployment decisions. It is a living population whose size changes through reproduction and mortality, managed by the coordinating system's biological maintenance protocol to stay within the range that the boring program's advance rate specification requires. The colony's reproduction rate is the biological parameter the coordinating system's management protocol most directly influences. The Litho-Crustacean's reproductive biology was specified for rapid population response to resource availability, a characteristic derived from the R-selected reproductive strategies of the marine invertebrates whose biology contributed to the design. Resource availability in the colony's context is the calcium carbonate debris rate at the bore face. High advance rate produces high debris rate, which produces high nutrition availability, which stimulates higher reproduction rate. The colony tends to self-regulate its size toward the population density that the available debris nutrition can support. The coordinating system's management protocol works with this self-regulation rather than against it. Rather than specifying a target population size and managing reproduction directly, which would require pharmaceutical intervention in the colony's reproductive biochemistry at a frequency the water chemistry management system would need to maintain continuously, the protocol manages resource availability to steer the self-regulation toward the target population size. If the colony's population census indicates a size below the boring program's advance rate specifications requirement, the coordinating system increases the advance rate instruction, driving more cavitation boring per unit time, producing more debris, stimulating higher reproduction through the increased nutrition. If the colony's population census indicates a size above the specification, the coordinating system reduces the advance rate instruction, lower debris rate, lower nutrition, slower reproduction until the colony's natural mortality rate reduces the population to specification. The population management through resource availability management is biologically stable. The colony cannot overshoot its food supply because the food supply is the coordinating system's controlled output. The coordinating system provides exactly the food the target population size requires. The population converges to the target from either direction without oscillation, because the resource availability signal that drives the colony's reproductive behavior is under the coordinating system's direct control at every update interval. The colony's mortality rate is managed through the bore zone's chemical environment. The Litho-Crustacean was specified for the freshwater zones and halocline zones chemistry, the cenote water's calcium bicarbonate chemistry and the halocline's modest salinity gradient. The anoxic zone's H2S chemistry, which attacks the organism's metabolic pathways through the same mechanisms that attack aerobic organisms generally, was not included in the design specification for the standard boring colony. Anoxic zone boring operations use a modified colony variant, the anoxic-grade Litho-Crustacean, whose metabolic pathways for energy generation and exoskeletal deposition operate in the absence of dissolved oxygen and tolerate the H2S concentrations the anoxic zone presents, whose biology is documented in Appendix F alongside the standard variants protocol. The transition between freshwater zone boring and halocline zone boring, the depth band where the colony advances through the halocline's salinity gradient, is managed by staged acclimation. The colony's chemosensory system detects the salinity change as it advances through the halocline, and the coordinating system monitors the colony's biological indicators, advance rate, paste output rate, reproductive activity, for signs of metabolic stress from the salinity transition. If the stress indicators cross the threshold, the coordinating system reduces the advance rate instruction to reduce the colony's metabolic demand during the acclimation period. When the stress indicators return to baseline, the advance rate returns to the specification. The halocline crossing is managed as a biological acclimation event, not as a construction schedule event. The construction schedule adapts to the biology's acclimation timeline. What the bore looks like from inside. A litho-crustacean bore is not a smooth-walled circular tunnel. The boring appendage's acoustic cavitation mechanism, which fractures at the grain boundary scale, produces a bore wall texture whose characteristic roughness is the calcium carbonate crystal grain size, typically 30 to 100 microns depending on the limestone's lithological character at the boring depth. After paste coating and cementation, the bore wall surface is smooth at the millimeter scale. The paste fills the roughness geometry produced by the grain-by-grain fracture, but retains a microtexture at the 10-micron scale that the crystal tube standard's anchor bracket specification uses as the primary surface preparation for chemical bonding. The microtexture provides mechanical interlocking sites for the fast-cure marine polymer grout at the anchor bracket interface that a polished bore wall would not provide. The bore cross-section is not precisely circular. The colony's formation-following behavior produces a bore whose cross-section follows the heading that the colony's aggregate advance direction produces at each boring session interval. The colony does not maintain a perfect compass heading. The chemical gradient steering produces a heading accuracy bounded by the gradient spatial resolution and the colony's aggregate chemosensory response characteristics. The bore's actual heading deviates from the specified heading by accumulated angular error at the rate the formation-following behavior's heading accuracy allows. The crystal tube standard's routing decision criteria account for this heading accuracy by specifying inter-synody routes with alignment tolerances derived from the boring program's historical heading accuracy statistics. A route that requires the bore to hit a target position within plus or minus 2 meters at 1 kilometer's advance is a route within the boring program's heading accuracy capability for the Yucatan standard limestone geology. A route requiring tighter alignment at the same distance is a route requiring intermediate course correction, the coordinating system introducing heading correction pulses through the chemical gradient at intervals that prevent the accumulated deviation from exceeding the tolerance. The bore diameter is not precisely equal to the crystal tube standard's required minimum bore diameter. The colony's boring swarm produces a bore whose diameter is the aggregate of each organism's boring appendage reach across the bore face. The colony's collective face coverage determines the bore diameter. The coordinating system manages the bore diameter by managing the colony's formation density at the bore face. A denser formation produces a wider bore, a sparser formation produces a narrower bore. The diameter specification is maintained by the formation density instruction, updated at each boring session, calibrated to the bore's recent diameter measurement from the transceiver chain's active ranging return at the bore face. The bore diameter is always slightly larger than the crystal tube standard's minimum requirement. The management protocol maintains a clearance margin that accounts for the diameter measurement's uncertainty and the crystal tube installation sequence's tolerance requirements. A bore that is at the minimum diameter is a bore where the crystal tube installation sequence has zero clearance for the alignment uncertainty the installation unit's positioning system produces. A bore with a clearance margin provides the alignment tolerance the installation sequence requires without risking the crystal tube section contacting the bore wall during the installation sequence's approach and seating operations. The biological-geological interface. The bore face is the civilization's most intimate contact with the formation's living geology. Not the crystal tube wall, which is a transparent barrier between the inhabited zone and the formation. Not the anchor pylon, which is a mechanical connection between the inhabited structure and the limestone. The bore face, where the Litho-Crustacean colony's boring appendages are at this moment advancing the civilization's frontier through limestone that has been forming for 66 million years, is the point where the civilization's biological instrument is directly, physically, grain by grain interacting with the formation's mineral structure. The bore face is the civilization speaking to the formation in the limestone's own language, biological mineral interaction, the same mode through which the cave system's entire passage network was produced. The cave passages that exist are the record of organisms interacting with limestone over geological time, not the same organisms and not the same timescale as the Litho-Crustacean colony, but the same fundamental mode. The Litho-Crustacean is the civilization's contribution to a conversation the formation has been having with biology since the Chicxulub impact opened the fracture networks that water and biology subsequently dissolved into the passage system the civilization inhabits. This is not a romantic framing. It is a geological description. The Litho-Crustacean's exoskeletal material, the biodeposited silicon carbide and biomineralized titanium accumulated from dissolved cenote minerals, is material the limestone originally contained as trace mineral inclusions. The organism extracts it from the water the limestone dissolves into, concentrates it in the exoskeleton, uses it for mechanical functions the boring operation requires, and eventually, when the organism dies and the exoskeleton is released back to the bore zone, returns it to the formation's mineral inventory. The organism does not permanently remove the limestone's mineral content. It borrows it, concentrates it into a useful mechanical form, uses it, and returns it. The formation's long-term mineral budget is unchanged by the boring program. The calcium carbonate paste the organism extrudes from the limestone debris it ingests is likewise a return to the formation, the same calcium carbonate the limestone is composed of, processed through the organism's biology and redeposited in a different location and a different microstructural form, but chemically equivalent to the material the bore face exposed. The boring program does not remove limestone from the cenote. It relocates it, from the bore face, where it was the limestone's solid matrix, to the bore wall, where it is the paste lining sealed surface. The limestone's total mass in the cenote remains constant. The boring program reorganizes it. A civilization that reorganizes the formation's material without removing it from the formation is a civilization that can expand its inhabited extent without depleting the material the formation is composed of. The boring program's geological impact is not material extraction, it is geometric reorganization of the same material that was already present. The passage that the boring program opens was not absent from the limestone before the bore arrived. The limestone occupied the space. The boring program relocates the limestone from the passage's future interior to the passage's wall lining. The passage appears where the limestone was. The limestone is in the lining. The formation's mass budget is unchanged. The formation's geometry has changed, a new passage exists where solid limestone was. The new passage's existence is PipeDream's civilizational act, the geometric reorganization of formation material from solid matrix to inhabited passage, executed by biology operating at the formation's own mineral interaction scale, sealed by the same organism's metabolic output from the same material it reorganized. The civilization opened the passage. The passage was always in the limestone, as potential. The boring program actualized the potential. The healing phase. The halt signals withdrawal of the colony from the bore face initiates the healing phase, the period during which the colony applies calcium carbonate paste to any exposed limestone surface that the boring session's advance left unsealed. The healing phase is not a repair operation triggered by a formation event. It is the standard conclusion of every boring session, whether the session ended by halt signal, advance rate target completion, or scheduled session boundary. Every boring session's conclusion includes the healing phase. The healing phase's duration is proportional to the boring session's length. More advance produces more bore wall surface requiring paste application. The coordinating system's boring session scheduling accounts for healing phase duration in the session length calculation. The session ends early enough that the healing phase can complete, the bore wall can be fully sealed, and the paste can achieve initial set before the next session begins. The healing phase's function is not cosmetic. It is the crystal tube standards installation sequence's prerequisite. The bore wall must be fully paste coated and at the initial set strength before the installation units enter the bore for crystal tube section positioning. An incompletely sealed bore wall, with exposed limestone surfaces that the paste has not yet covered, is a bore wall that the installation unit's anchor bracket placement could inadvertently damage by contacting the unsupported limestone surface with positioning forces that exceed the unsupported limestone's contact strength. The healing phase ensures that the entire bore wall the installation units will work against is paste coated and sealed before the installation units enter the bore. The coordinating system's healing phase confirmation comes from the colony status monitor, the biological monitoring network's detection of the colony's transition from the active boring phase's bioluminescent signal pattern to the healing phase's signal pattern, and subsequently from the transition to the resting phase's signal pattern that indicates healing completion. The boring phase, the healing phase, and the resting phase produce distinct bioluminescent signal signatures that the transceiver chain's optical sensors detect and the coordinating system's biological management layer interprets as operational status flags. The installation unit deployment instruction is gated on the colony's resting phase confirmation. The coordinating system does not advance the installation units until the colony's bioluminescent signature confirms healing completion. The colony also heals itself during the healing phase. The boring appendage's sustained acoustic cavitation operation during the boring session produces mechanical fatigue in the appendage structures. The oscillating elements that generate the cavitation field experience cyclic stress loading at the oscillation frequency throughout the boring session. The appendage's material, the bioengineered chitin silicon carbide composite that the organism deposits during its developmental phase, has a finite fatigue life under this cyclic loading. The healing phase includes a biological repair cycle in the boring appendages. The organism's repair biology dissolves the most fatigued material at the highest stress appendage locations and redeposits fresh composite material from the mineral ions dissolved in the bore water. The appendage is not replaced. It is repaired at the molecular scale during each healing phase. The repair rate limits the boring session length from the organism's side independently of the coordinating system's schedule management. A boring session that exceeds the repair rate's ability to restore the appendage's fatigue life between sessions is a boring session that progressively degrades the appendage's mechanical integrity, and by extension, the colony's boring effectiveness, across successive sessions. The coordinating system's boring session scheduling includes an appendage fatigue model that predicts the repair rate's capacity as a function of the session length, the advance rate, and the limestone's hardness at the current boring front's geological zone. Sessions that would exceed the repair rate's capacity are shortened. The shortened sessions reduce the advance rate's instantaneous output but preserve the advance rate's sustainable output over the boring program's full duration. A colony that preserves its boring appendage integrity through disciplined session management outperforms a colony that maximizes individual session output at the cost of progressive appendage degradation. The advance rate that matters to the construction schedule is the sustainable advance rate across the boring program's full duration, not the maximum rate achievable in any individual session at the cost of the subsequent session's capacity. The coordinating system session scheduling is optimized for sustainable advance rate, not for individual session output. Colony generations across the design life. The Litho-Crustacean colony that will bore the regional network's inter-synody connections in year 500 of the installation is not the colony that bored the founding module's first anchor grouting channels in year 1. The organisms that constituted the founding colony have completed their reproductive cycles, aged, died, and been replaced by successive generations many times over in 500 years. The colony's genetic identity, the engineered genetic architecture that produces the boring appendage biology, the exoskeletal deposition chemistry, the paste output metabolism, the bioluminescent coordination signaling, the chemosensory steering response, persists across generations through faithful biological reproduction. The colony is genetically continuous across the full design life. The individuals are not. The genetic continuity is managed by the Biological Maintenance Protocol's Genetic Drift Monitoring Program. Genetic drift, the random accumulation of neutral mutations in a finite population across generations, can, over sufficient generational time, alter gene frequencies in ways that shift the colony's functional characteristics from their design specifications. The monitoring program tracks the engineered genetic loci that determine the boring appendage's oscillation frequency range, the exoskeletal deposition chemistry's mineral ratios, the chemosensory steering response's sensitivity to the route guidance compound, and the halt signal's priority response pathway. These functional loci are the colony's engineered core, the characteristics whose maintenance is the Biological Maintenance Protocol's primary genetic management objective. When the genetic drift monitoring identifies a significant frequency shift at any monitored locus, a shift that the coordinating system's functional model projects will produce a functional characteristic outside the specification range within the next generation, the protocol's genetic management response is colony recruitment from the master genetic archive. The Master Genetic Archive holds reproductively viable specimens of the founding colony's genetic composition, cryogenically preserved at the Formation Cenote's Deep Gallery Research Facility. A small number of archive specimens are thawed, reproduced, and introduced to the active colony's breeding population, diluting the drifted locus frequency back toward the founding specification. The archive is not a backup colony. It is a genetic reference library, the founding specification preserved in biological form, accessible for the genetic correction events the drift monitoring triggers. The archive does not bore. It does not produce paste. It does not advance the frontier. It preserves the genetic architecture that the active colony uses to bore and paste and advance. The archive's function is to ensure that what the founding generation designed into the colony's genome is still present in the colony's active population across the full 1,000-year design life. The archive specimens are renewed on a biological schedule, the cryogenic preservation's technical limitations on specimen viability duration requiring periodic renewal from the active colony's genetically verified individuals. The renewal cycle is managed by the Biological Maintenance Protocol, which identifies individuals in the active colony whose genotype at the monitored loci matches the founding specification within the tolerance the genetic monitoring program's analysis specifies, extracts breeding material from these individuals, produces cryogenic specimens from the extracted material, and replaces the oldest specimens in the archive with the new ones. The master genetic archive is the biological equivalent of the digital twin's construction knowledge layer, the founding specification preserved in a medium that does not degrade with time, accessible for correction when the active system's drift from specification requires it. The digital twin preserves the construction specification in data. The genetic archive preserves the biological specification in biology. Both serve the same function, maintaining the founding design's accuracy across the generational transitions that the 1,000-year design life requires. The Litho-Crustacean as geological actor. At the scale of the Litho-Crustacean's individual biology, the organism is a metabolic machine executing the biochemical cycles the founding biologists specified. At the scale of the colony's boring program, the colony is the civilization's frontier instrument, the mechanism by which the habitable network expands into previously inaccessible limestone. At the scale of the formation's geological history, the boring program is the civilization's contribution to the process that has been reorganizing the Yucatan's limestone for 66 million years. The formation's passage network exists because water, biology, and time have been reorganizing calcium carbonate since the Chicxulub impact created the fracture structure that dissolution then enlarged. The Litho-Crustacean boring program is that process, accelerated, directed, and managed by a civilization that is simultaneously the process's beneficiary and its steward. The organisms are engineered, but the chemistry is the same chemistry. The bores are planned, but the mineral interactions are the same mineral interactions. The pace is accelerated, decades rather than millennia for the same passage volumes, but the geological product is indistinguishable from what the formation would produce on its own schedule. A Terraform operator conducting a geological survey of the boring program's completed bores, comparing the bore wall's paste-sealed surface to the adjacent unmodified limestone surfaces, can determine that the boring program produced the bore rather than geological dissolution. The bore's geometry is more regular, the paste lining's texture is different from dissolution's gradual surface, the bore diameter is more consistent than dissolution-produced passages. The bore is not a geological passage. It is a civilizational passage. The distinction is legible to a geologist with appropriate instrumentation. In 10,000 years, without the civilizational context that makes the distinction legible, the distinction will have disappeared. The paste lining will have undergone diagenetic recrystallization, the same geological transformation that converts freshly deposited calcium carbonate to the mature calcite and aragonite phases that characterize the cenote's natural limestone. The bore's geometry will have been modified by the same geological dissolution processes that shaped the natural passages. The boring program's microtexture at the bore wall will have been smoothed by 10,000 years of water chemistry working on the recrystallized paste. The geological record will show a passage network that expanded in the period when PipeDream occupied the cenote, a rapid expansion relative to the natural dissolution rate, legible as a civilization's presence, but the material difference between the boring program's passages and the natural dissolution passages will have disappeared into the limestone's ongoing geological transformation. The civilization's tunnels become the formation's passages. The formation accepts the reorganization. The boring program's work is absorbed into the limestone's geological history as one more episode of biological mineral interaction that the formation's 66 million year record of biological mineral interaction accommodates. The civilization passes. The formation continues. The passages remain, indistinguishable eventually from the passages that 66 million years of dissolution produced without civilizational direction. The Litho-Crustacean's biological boring, which the founding engineers designed to work in the formation's own biological mineral language, left work that the formation, in geological time, will make its own. This is the deepest expression of aquaforming. Not just infrastructure that conforms to the formation while the civilization operates it. Infrastructure whose material composition is the formation's own material, reorganized by the formation's own biological chemical processes, reintegrating into the formation's geological history at the geological timescale the formation operates on. The civilization builds inside the formation. The formation reclaims the construction. The passage remains. The civilization passed through. The limestone accepted it. The acceptance is recorded in the passage geometry, preserved in the geological record, indistinguishable from 66 million years of the same acceptance of the same biological mineral process working through different agents over different timescales toward the same material outcome. Calcium carbonate, reorganized by biology, sealed by the organism's own metabolic output, integrated into the limestone formation that produced the organism's nutrition, preserved by the formation's geological continuity across the timescales that make the distinction between the civilization's passage and the formation's passage irrelevant. The boring program is geology. The Litho-Crustacean is geology. The civilization that designed it, managed it, and inhabited the passages it made is, from the formation's geological perspective, one more biological agent that interacted with the limestone for a period and then was absorbed into the geological record with everything else that has interacted with it since the Chicxulub impact produced the fractures that everything, the water, the organisms, the civilization, the Litho-Crustacean, has been interacting with ever since. The formation is patient. The limestone was here before the Litho-Crustacean. The limestone will be here after the civilization. The boring program is the brief period when the civilization asked the limestone if it could make some passages. The paste lining is the limestone's answer. The passage is the agreement. Cross-references, Part 1, CH2, Y cenotes, Part 3, CH1, Rivers Beneath the Jungle, Part 3, CH3, Linking cenote to cenote, Part 4, CH1, The Robot Frontier Core, Part 4, CH2, Autonomous Construction, Part 4, CH4, Swarm Engineering, Part 4, CH6, Biological Civil Engineering, Part 5, CH2, Limestone Crustaceans. For Litho-Crustacean Standard Variant Genetic Specification and Founding Archive Maintenance Protocol, see Appendix F, Biological Operations Manual. For anoxic grade variant specification and halocline acclimation management protocol, see Appendix F, Biological Operations Manual. For boring appendage oscillation frequency calibration by lithological zone and geological model integration protocol, see Appendix D, Construction Operations Manual. For halt signal chemical compound specification and seismic precursor detection threshold calibration, see Appendix A, Formation Baseline Protocol. For boring session scheduling parameters and appendage fatigue model inputs, see Appendix D, Construction Operations Manual. PipeDream. Part 4, Machines that Build Themselves. Chapter 6, Biological Civil Engineering. Civil engineering is the discipline of organizing physical materials into structures that serve human habitation and movement. The surface world practices it in concrete and steel and asphalt, materials that are manufactured, transported, placed, and maintained by a workforce of specialized humans operating specialized equipment according to designs produced by specialized professionals. The materials are inert. The structures they constitute are inert. The maintenance that keeps them serviceable is external, applied from outside the structure by agents that have no metabolic relationship to the material they are maintaining. The structure does not participate in its own upkeep. It receives upkeep. The structure does not know when it needs maintenance. The monitoring system that detects maintenance needs is external to the structure's own material. This is the civil engineering paradigm the surface world has operated within for several thousand years. Its products are everywhere: roads, bridges, dams, sewers, water mains, foundations, retaining walls. All of them inert. All of them maintained from outside. All of them degrading continuously from the moment of construction toward the moment when the maintenance cost of continued operation exceeds the replacement cost of new construction. PipeDream practices a different discipline. Not as a philosophical position against the surface world's paradigm, but as a practical consequence of the cenote environment's conditions. The cenote does not offer the surface world civil engineering paradigm's prerequisites: flat, stable, accessible ground on which to place and cure concrete, atmospheric conditions in which steel fabrication and welding can be performed, a human workforce that can be present throughout the construction and maintenance operations without extraordinary life support. The cenote offers none of these. The cenote offers water, limestone, biological communities, and geological time. The civil engineering paradigm that works in the cenote is the one that uses what the cenote offers. Biological civil engineering is the practice of designing, deploying, and managing living organisms as primary infrastructure components, not as supplements to inert infrastructure, not as biological curiosities alongside the real engineering, but as the primary material of the installation's maintenance and expansion systems. The organisms are the engineers. The organisms are the maintenance crew. The organisms are the construction material and the construction tool simultaneously. The organisms improve with time rather than degrading with it. The organisms reproduce their own capability rather than requiring external replacement when individual capacity is consumed. The surface world has no civil engineering discipline that treats organisms as primary infrastructure. It treats organisms as problems to be managed: the biofilm the pipelining must resist, the tree roots the sewer must exclude, the marine growth the ship hull must shed. PipeDream's biological civil engineering inverts this: the organisms are the infrastructure. The biofilm is not the enemy of the pipe's optical surface. The biofilm management is the system, and the Ancistrus vitreous colony is the system's primary component. The organisms are not problems the infrastructure must manage. They are the management. The 3 tiers of biological civil engineering. PipeDream's biological civil engineering operates across 3 tiers that correspond to the 3 scales at which biological systems interact with the installation's physical infrastructure: the molecular scale, where biological chemistry interacts with material surfaces; the organismal scale, where individual organisms or small groups perform discrete maintenance, construction, or sensing functions, and the ecological scale, where biological communities perform system-level functions that no individual organism and no collection of individual organisms operating independently could achieve. The molecular tier is the most pervasive and the least visible. The fast-cure marine polymer grout that bonds the anchor pylons to the limestone is a biological product. The polymer's precursor compounds are produced by bacterial fermentation in the coordinating system's biological production facility at the formation cenotes processing hub. The polymer's specific molecular architecture, the chain length, the cross-linking density, the surface chemistry groups that produce the bond to calcium carbonate substrate, was specified through directed evolution of the bacterial production pathway over a 7-generation optimization protocol before the founding module's installation. The material the anchor pylon rests in was made by bacteria, optimized through biological evolution, and is maintained in functional form by the same bacterial community that produces it, which colonizes the grout interface and produces a biofilm whose chemistry is the grout's chemical stability layer. The grout does not degrade in the formation environment because the bacterial community at the grout-limestone interface is producing the chemistry that maintains the grout's cross-link density against the dissolution chemistry the cenote water would otherwise apply. The grout's biological production and biological maintenance are aspects of the same bacterial metabolic cycle. The material cannot be separated from the biology that made it and maintains it. It was designed to be inseparable. The mycofiltration panel operates at the molecular tier. The fungal network's enzymatic degradation of surfactants and personal care compounds is a molecular scale process whose products, the small organic acid molecules and mineral ions that the enzymatic breakdown produces, are directly bioavailable to the food forest's root mycorrhizal network in the soil above the cenote rim. The molecule that was a surfactant in the gray water stream is a soil amendment nutrient in the food forest's mineral cycle by the time the mycofiltration process and the food forest's microbial processing have transformed it. The molecular scale biological transformation is the connection between the inhabited zone's waste stream and the ecological zone's nutrient cycle. The organismal tier, the Litho-Crustacean colony, the Ancestris vitreous schools, the squeegeebot fleet as mechanical analog, the pink dolphins as survey instruments, has been documented extensively in the preceding chapters and in the biological systems documentation the master context brief establishes. The organismal tier civil engineering functions are the most recognizable to an observer familiar with the installation. These are organisms doing specific tasks that the installation requires, managed by the coordinating system, performing functions that mechanical equipment would perform less effectively or at greater cost if biological performance were not available. The ecological tier is the tier that the surface world civil engineering has never accessed, because the surface world civil engineering paradigm has no mechanism for deploying ecological processes as engineering functions. An ecological process is a system-level behavior produced by the interactions of many organisms and many non-living components across spatial scales and temporal scales that no engineering specification can fully describe. The food forest succession is not a specified engineering output. The cenote's biological community succession is not a specified engineering output. They are system-level processes whose civil engineering functions, soil stabilization, nutrient cycling, thermal management, water quality maintenance, biological corridor function, emerge from the accumulated interactions of hundreds of species in millions of individuals across decades of ecological maturation. The civil engineering value of these ecological tier processes is proportional to the ecological maturity they have achieved. A food forest in its first year produces modest soil amendment, minimal canopy management, negligible mycorrhizal network soil processing capacity. A food forest in its 30th year produces substantial soil amendment, effective canopy management, and a mycorrhizal network dense enough to reduce the irrigation requirement by the fraction that the network's water retention capacity provides. The civil engineering capability of the ecological tier is a time integral. It accumulates with ecological maturation and cannot be purchased at any price at the installation's founding. It can only be invested in, at year one, with the patient expectation that the ecological return on that investment compounds through ecological time. PipeDream's biological civil engineering strategy treats ecological time as an asset class. The founding investment in the food forest's pioneer succession, the Litho-Crustacean colony's initial habitat establishment, the Ancestris vitreous population's initial introduction to the freshwater zone, these investments generate compound returns as ecological maturation deepens the capability of each biological system across the design life. The biological infrastructure that is most capable at year 500 is not the infrastructure that was installed at highest initial cost. It is the infrastructure that was established earliest and maintained most faithfully, the infrastructure with the longest ecological maturation history. The designed organism as infrastructure class. The surface world's infrastructure taxonomy has many classes: structural systems, mechanical systems, electrical systems, plumbing systems, envelope systems. The designed organism is not a class in any of these taxonomies. It is not treated as infrastructure at all. It is treated, where it appears in surface world engineering contexts, as a biological supplement to the primary engineering system, a curiosity, a demonstration project, an innovation pilot that the next facility will adopt if this one works out. It is never the primary system. PipeDream's infrastructure taxonomy includes designed organisms as a primary class alongside crystal tube sections, anchor pylons, and maglev propulsion rails. The designed organism class has its own specification format in the construction management system, its own maintenance protocol in the biological operations manual, its own performance monitoring in the coordinating systems sensor network, and its own quality assurance in the genetic drift monitoring program. The designed organism is procured, deployed, monitored, and maintained with the same administrative rigor as any mechanical component in the installation, through a different administrative mechanism. Because the procurement is a breeding protocol rather than a manufacturing order, the deployment is a habitat establishment protocol rather than an installation sequence, and the maintenance is a biological management protocol rather than a cartridge replacement procedure. The rigor is identical. The mechanism is appropriate to the organism's biological nature. The specification format for a designed organism includes parameters that no mechanical component specification would include: reproductive rate, generation time, genetic drift monitoring loci, habitat requirements by season, predator-prey relationships with other species in the managed biological community, behavioral response characteristics to the coordinating system's management signals, and the genetic archive protocol for the founding genotypes preservation. These parameters determine the organism's performance as infrastructure in the same way that a mechanical component's tensile strength, corrosion resistance, and service temperature determine the mechanical component's performance. The organism's specification is different in kind from the mechanical component's specification because the organism's performance is biological in kind. The specification format is designed for the kind of infrastructure being specified. The designed organism as infrastructure class has two properties that no mechanical component class shares. The first is self-reproduction. The organism produces its own replacement through biological reproduction, eliminating the procurement and manufacturing cycle that every mechanical component's replacement requires. The Ancestris vitreous colony that is maintaining the crystal tube walls in year 500 was not manufactured at year 500. It reproduced itself from the founding colony introduced at year 1, through hundreds of generations of biological reproduction, maintaining the genetic characteristics the founding generation was designed for through the genetic drift monitoring program's management. The colony's replacement cost is the genetic drift monitoring program's cost, the habitat maintenance cost, and the archive renewal cost, all substantially lower than the manufacturing and procurement cost of an equivalent mechanical cleaning fleet producing the same cleaning coverage. The second property is ecological integration. The designed organism interacts with other organisms in the managed biological community in ways that mechanical components do not interact with each other. The Ancestris vitreous colony's enzymatic cleaning activity affects the biofilm community's succession on the tube walls. The biofilm community's succession affects the dissolved organic carbon budget in the freshwater zone's water column. The dissolved organic carbon budget affects the water chemistry that the mycofiltration panels process in the gray water circuit. The mycofiltration panel's output affects the food forest soil chemistry. The food forest soil chemistry affects the water table chemistry that the ballast circuit receives. Every designed organism in the installation is connected to every other organism and to the installation's mechanical systems through these ecological interaction chains. The connections produce behaviors that no individual organism's specification describes, system-level functions that emerge from the aggregate of ecological interactions. The civil engineering value of these emergent system-level functions, the water quality maintenance that the aggregate biological community provides, the nutrient cycling that connects the gray water circuit to the food forest's productivity, the thermal management that the food forest's canopy provides to the cenote's air column, is not in any individual organism's specification. It is in the ecological network specification, the managed species composition, the habitat conditions that maintain the specified species in specified abundances, and the interaction chains that produce the civil engineering functions the ecological network provides. The coordinating system's biological management layer manages the ecological network as a system, monitoring the interaction chain's health indicators, adjusting the habitat conditions that maintain the specified species composition, intervening in the interaction chain where the monitoring identifies a developing imbalance. The management target is not the individual organism's performance. It is the ecological network's system-level civil engineering output, the water quality, the nutrient cycling, the thermal management, the biological corridor function, the survey coverage the dolphin population provides. These outputs are the civil engineering products the biological management layer is responsible for. The organisms are the mechanism. The outputs are the infrastructure function. The governance of designed biology. Designed organisms introduce governance challenges that mechanical infrastructure does not present. A crystal tube section that is performing below crystal specification is a maintenance problem. Identify the cause, execute the remediation, restore performance. The crystal tube section does not have interests, does not reproduce, does not interact with adjacent crystal tube sections in ways that affect their performance, and does not evolve in response to the management actions applied to it. A designed organism that is performing below specification may be doing so because its genetic architecture has drifted from the founding specification, because its habitat conditions have changed in ways the biological management protocol has not yet compensated for, because a disease event is affecting its population, because an interaction with another species in the managed biological community has altered its behavior, or because the organism's own evolution, the random mutation and natural selection that biological reproduction produces even in managed populations, has produced a variant that the current management protocol does not support. All of these causes require different responses. Some require the genetic archives founding genotype introduction. Some require habitat condition adjustment. Some require veterinary intervention. Some require the managed biological community species composition adjustment. Some require the biological management protocol's revision. The governance challenge is that the designed organism's performance is not fully controllable by the management actions the coordinating system can take. The organism is a biological entity that responds to management within its biological nature's constraints. It does not simply do what the coordinating system specifies in the way the swarm unit does what the coordinating system instructs. The organism's response to the coordinating system's management signals is probabilistic, influenced by its current biological state, its population's genetic composition, its habitat conditions, and its interactions with other organisms. The coordinating system manages toward outcomes, not toward specific behaviors. This governance uncertainty is the designed organism's fundamental difference from the mechanical component as an infrastructure class. The mechanical component performs within its specification or fails. The designed organism performs within a range whose bounds the biological management protocol establishes but whose specific trajectory within those bounds the organism's biology determines. The governance of designed biology is the management of biological systems towards civil engineering outcomes under the uncertainty that biological variability introduces. The Redeemer governance framework addresses this uncertainty at the constitutional level through the Terraform Operators concurrent authority structure. The Terraform Operator, trained in ecological succession management before formation monitoring, holds the authority to halt any construction or expansion operation when the biological system's performance has moved outside the parameter range that the current management protocol can address without Terraform Operator review. The parameter range is specified in the Biological Operations Manual for each designed organism class. The Terraform Operator's authority is triggered when the monitoring identifies a condition outside the parameter range and the coordinating system cannot generate a management response within the protocol's specified response envelope. The Terraform Operator's biological management authority is not the authority to redesign the organism or to revise the biological management protocol. The Terraform Operator's authority is the authority to halt the operations that depend on the biological system's performance, convene the biological management review that the deviation from specification requires, and resume operations only when the review has produced a management response that the coordinating system can implement within the revised protocol's revised envelope. The biological management review is a formal process under the Redeemer framework. The Terraform Operators of all affected installations, the coordinating system's biological management analysis, the genetic archive's current genotype comparison with the active population, and the biological community interaction chain analysis that identifies whether the deviation is an individual species performance issue or a community-level interaction issue. The review produces either a protocol revision, if the deviation is within the biological management layer's competence to address through adjusted management actions, or an escalation to the Network Governance Council, if the deviation indicates a fundamental departure from the biological system's design specification that requires founding genotype reintroduction or species composition revision. The escalation to the Network Governance Council involves the commons ownership principle. The biological specifications and genetic archives are commons assets, not proprietary assets of any founding shareholder or governance council. No single entity can authorize a modification to the designed organism's fundamental specification. The Network Governance Council's authorization, with the Research Commons scientific review, is required. The process is slow by construction. It is designed to be slow, because a hasty modification to a designed organism's fundamental specification could introduce unforeseen consequences in the ecological interaction chains that the review process's thoroughness is intended to prevent. The designed organism's governance is the governance of the formation's living infrastructure, and the formation's living infrastructure, as the commons ownership principle establishes, belongs to no one. It is the Principality's commons, managed by the coordinating system and the Terraform Operators on behalf of the Principality's citizenry, subject to the Redeemer framework's constitutional constraints, and protected from the concentration of control that would allow any single interest to modify the biological commons for private benefit. The governance of designed biology is ultimately the governance of the relationship between the civilization and the formation, the same relationship that the aquaforming doctrine defines and the 1,000-year design life requires to be maintained faithfully across every generational transition the Principality undergoes. The designed organism is the living expression of that relationship, biology designed for the formation's conditions, managed by the civilization's intelligence, performing civil engineering functions that neither the formation alone nor the civilization alone could achieve. The governance of designed biology is the governance of this partnership. What biological civil engineering produces that mechanical civil engineering cannot? The capacity for self-repair is the property that most distinguishes biological civil engineering products from mechanical civil engineering products. The litho-crustacean boring appendage's fatigue repair during the healing phase, the molecular scale dissolution and redeposition of the appendage material at the highest stress locations, is a repair operation that the appendage performs on itself, without external intervention, using the mineral resources dissolved in the bore water, driven by the organism's own metabolic energy. The appendage does not require a maintenance crew, a replacement cartridge, a maintenance hub visit, or any external input to maintain its functional integrity. It maintains itself by being alive. No mechanical component maintains itself. The mechanical component degrades from the moment of installation. The degradation rate is managed by the maintenance system's interventions, lubrication, cleaning, cooling, replacement, but the degradation direction is always toward failure. The mechanical component does not repair itself during use. It wears. The maintenance system repairs the accumulated wear at intervals. Between maintenance intervals, the wear continues. The biological component degrades during the boring session and repairs during the healing phase. The degradation and the repair are the same operational cycle. The organism cannot bore without fatiguing the appendage, and the organism cannot heal without consuming the bore session's nutrition to fuel the repair metabolism. The degradation and the repair are metabolically coupled. The organism's biology does not separate them. The boring program schedule separates them, the session and the healing phase alternate, but the biology is a continuous cycle that the schedule structures, not a unidirectional degradation that the schedule manages. A civil engineering component that self-repairs during its operational cycle has a sustainable service life that the component's regeneration rate determines, not the material's fatigue life. The litho-crustacean boring appendage's sustainable service life is not the number of cavitation cycles the material can sustain before fatigue failure. That limit would produce a defined service life after which replacement is required. The sustainable service life is the number of boring sessions the organism can sustain while the healing phase maintains the appendage material above the minimum functional threshold, which is determined by the organism's metabolic rate and the bore zone's mineral availability, both of which the biological management protocol maintains within the range that supports functional regeneration. The appendage's service life is indefinite as long as the metabolic conditions support regeneration. This is the biological civil engineering product's most significant advantage over the mechanical civil engineering product in a 1,000-year design life context. The mechanical product's service life is finite and depleted continuously from installation. The biological product's service life is indefinite, maintained by the organism's own metabolic processes, as long as the habitat conditions that support those processes are maintained. The maintenance investment that sustains the biological product's function is the habitat maintenance investment, fundamentally different in kind and in cost from the mechanical replacement investment that sustains the mechanical product's function. The ecological maturation benefit compounds this advantage at the ecological tier. The ecosystem that the biological civil engineering maintains is not a static system that requires constant energy input to maintain against thermodynamic decay. It is a successional system that advances toward greater organizational complexity, greater productivity per unit of resource input, and greater resilience against perturbation with each year of ecological maturation. The food forest at year 30 is not the food forest at year 1 with 30 years wear. It is a substantially more productive, more self-maintaining, more disturbance-resistant system that produces more civil engineering benefit, more soil stability, more nutrient cycling, more thermal management, more water retention, than the year 1 system produced, at the same or lower management cost, because ecological maturation has increased the ecosystem's own self-organizing capacity. Mechanical civil engineering produces products whose performance is highest at installation and decreases continuously thereafter. Biological civil engineering produces products whose performance at the ecological tier is lowest at installation and increases continuously through ecological maturation until the system reaches climax ecology. The investment timing is reversed. Mechanical civil engineering's highest performance is at the beginning of the design life, declining toward the end. Biological civil engineering's highest performance is toward the middle and end of the design life, after the ecological maturation period has run. This reversal is the strategic advantage that the 1,000-year design life amplifies. A mechanical civil engineering installation operating for 1,000 years spends its first decades in high performance and its remaining decades in declining performance with increasing maintenance cost. A biological civil engineering installation operating for 1,000 years spends its first decades establishing the ecological foundations that produce increasing performance through the middle centuries, the most ecologically complex and most productive period of the design life, before the final century's gradual transition to the climax ecology's stable but highest total productivity state. The 1,000-year design life is the minimum duration at which biological civil engineering's compounding ecological maturation advantage fully manifests. A surface world development model with a 30-year investment horizon cannot capture biological civil engineering's ecological return. The ecological maturation period is too long relative to the investment horizon. PipeDream's founding shareholders' acceptance of the 1,000-year design life was simultaneously the acceptance of the investment horizon at which biological civil engineering's advantages become the dominant civil engineering paradigm. The economics of biological civil engineering require geological patience. The founding charter's governance architecture was designed to enforce geological patience across generational transitions. The investment thesis and the governance architecture were designed together, because the investment thesis only produces its returns under the governance architecture that maintains the biological investment's habitat conditions across the timescale the returns require. The mycelial infrastructure. The mycofiltration panel's fungal network is the installation's most metabolically active biological civil engineering component and the least visible. The fungal network operates inside the panel's substrate, not on the substrate's surface, not in the water column, not in a space that any sensor except the water chemistry proxy measurements accesses directly. The fungal network's civil engineering function, processing the gray water stream's organic load, happens at the molecular scale within the panel's interior, invisible to any direct optical or acoustic monitoring. The water chemistry proxy measurements are the coordinating system's primary monitoring interface with the mycofiltration panel's fungal network. The panel's influent chemistry, the gray water stream's dissolved organic carbon content, surfactant concentration, and personal care compound load, is measured upstream of the panel. The panel's effluent chemistry, the processed water's chemistry after the fungal network has metabolized the organic load, is measured downstream. The difference between influent and effluent chemistry is the network's processing efficiency, the fraction of the incoming organic load that the fungal network has metabolized in the residence time the panel geometry provides. Processing efficiency is the fungal network's primary performance indicator. A network at full functional capacity processes the incoming organic load within the panel's hydraulic residence time, producing effluent chemistry within the ballast circuit specification. A network approaching the end of its substrate's nutrient availability, the network's growth front having consumed the substrate's accessible nutrition, produces declining processing efficiency as the least nutrient-depleted substrate zones concentrate the remaining active fungal growth in a fraction of the panel's full volume. The efficiency decline is measurable before it crosses the ballast circuit specification's threshold, giving the coordinating system the advance warning the condition-based maintenance model requires. The mycofiltration panel civil engineering function extends beyond the gray water processing it was specified for. The fungal network's mycelial extension, the microscopic filaments the fungus produces to explore new substrate zones for nutrition, penetrates the panel's porous substrate in a fractal branching pattern that dramatically increases the effective surface area per unit volume available for enzymatic chemistry. The same fractal architecture that makes the fungal network metabolically efficient as a filter also makes the fungal biomass physically structured in a way that the soil amendment application exploits. The fungal biomass harvested from the panel carries the mycelial network's fractal structure into the food forest soil, where it provides immediate physical structure for the soil's pore network. The pores that the fungal biomass creates as it decomposes maintain the soil's water retention capacity for the period it takes the food forest's native mycorrhizal network to establish through the same soil zone. The mycofiltration panel is not only a gray water filter. It is a soil amendment production system whose product, the harvested fungal biomass, performs soil engineering functions in the food forest that the filter's primary function generates as a metabolic byproduct. The filter processes gray water. The processing produces biomass. The biomass engineers soil. 3 civil engineering functions from one biological component: water processing, biomass production, soil engineering. The molecular tier biology connects to the ecological tier outcomes through the fungal metabolic cycle. The mycelial network is also the installation's biological intelligence infrastructure at the soil scale. The food forest mycorrhizal network, the below-ground fungal network that connects the food forest's plant root systems into a nutrient-sharing community, was established from the mycofiltration panel harvest material. The mycorrhizal network is genetically related to the mycofiltration network, produced by the same fungal species the panel was inoculated with, extended into the soil environment from the same biological source. The food forest soil intelligence, the mycorrhizal network's capacity to redistribute nutrients from resource-rich zones to resource-limited zones, supporting the weakest members of the plant community at the expense of the strongest, maintaining species diversity by preventing competitive exclusion, is the civil engineering function the mycofiltration panel seeded into the food forest soil. The food forest species diversity is a civil engineering output. Diverse species composition produces diverse root architecture, different species penetrating to different depths, maintaining the soil's physical structure through different mechanical mechanisms. Diverse species composition produces diverse canopy architecture, different species achieving different heights, creating the layered canopy that the cenote's thermal management requires. Diverse species composition produces diverse phenological timing, different species producing nutritious fruit and leaf material at different seasons, maintaining continuous food production across the annual cycle. All of these are civil engineering outputs of the mycorrhizal network species diversity maintenance. The fungal network is the civil engineer. The species diversity is the engineering output. The soil amendments and the management protocol are the inputs. The civil engineering product is the productive, stable, thermally effective, water-retaining food forest canopy that the cenote opening requires. Biological infrastructure that predates PipeDream. Not all of the biological civil engineering infrastructure PipeDream manages was designed by PipeDream's founding biologists. Some of it was already present in the cenote when the hydroprint sensors arrived. The cave biological community that the hydroprint surveys documented across the freshwater zone, the halocline zone, and the anoxic zone, the species that have been present in the cenote's biological community since before any human had descended into it, is infrastructure that 66 million years of evolutionary diversification and ecological succession produced without civilizational management. The sulfate-reducing bacteria in the anoxic zone that the chemostat's industrial metabolism is built on are not designed organisms. They are wild organisms, occupying the ecological niche that the anoxic zone's chemistry provides, performing the metabolic functions they evolved to perform under the chemical conditions they evolved within. PipeDream's relationship to this pre-existing biological infrastructure is the most delicate governance challenge in the biological civil engineering domain. The wild organisms cannot be specified as infrastructure in the way the designed organisms are specified. They cannot be genetically archived and restored to specification when drift occurs. They cannot be managed toward performance targets through the chemical gradient signals and population management protocols that work for the designed organisms. They can only be managed indirectly, by maintaining the habitat conditions that support their ecological function and by not introducing conditions that disrupt their ecological function. The Terraform Operators' management authority over the pre-existing biological community is accordingly different from their authority over the designed organisms. With designed organisms, the Terraform Operators manage toward performance specifications derived from the organism's engineering design. With pre-existing organisms, the Terraform Operators manage toward habitat condition specifications derived from the organism's ecological requirements, maintaining the water chemistry, temperature, pressure, and biological community composition that the organisms require to perform their ecological functions. The performance is the ecological function the organisms have been performing since before the civilization arrived. The management objective is to not disrupt it. This is the aquaforming doctrine applied to biology. The biological infrastructure conforms to the formation rather than the formation conforming to the biological infrastructure. The pre-existing organisms are the formation's biological expression. The civilization's civil engineering manages around them, not over them. The chemostat's industrial metabolism is built on the wild anaerobic bacterial community's natural metabolic function, not on a redesigned bacterial community optimized for industrial throughput, but on the natural community performing the same function it has always performed, managed by the coordinating system's harvest timing and depth control to maximize the civilization's access to the metabolic output without disrupting the biological community's ecological function that produces it. The electrochemical harvest system's microbial fuel cells operate through the same principle. The sulfate-reducing bacteria and methanogens that transfer electrons from organic matter oxidation through the fuel cell circuit are wild organisms performing their natural metabolic function. The fuel cell's anode is placed in their environment. The electrons they transfer in the course of their natural metabolism now flow through the circuit rather than into the sediment. The organisms are unaware of the change. Their metabolism is unchanged. The civilization has connected a wire to a metabolic process that was already happening and will continue to happen regardless of whether the wire is connected. Biological civil engineering at the pre-existing organism tier is not management of organisms. It is management of connections to organisms, connections that the civilization's infrastructure establishes to access the metabolic outputs that the organisms produce independent of the civilization's presence. The organism does not work for the civilization. The civilization works around the organism. The connection is the civilization's civil engineering. The metabolic output is the organism's biology. The biological maintenance of the biological infrastructure. The designed biological infrastructure requires biological maintenance in addition to the coordinating systems management. The Ancestris vitreous colony maintains itself through reproduction and the individual organism's immune system and metabolic health. The Litho-Crustacean colony maintains itself through the healing phase and the colony's population management response to resource availability. The food forest maintains itself through the mycorrhizal network's nutrient redistribution and the ecological succession's progressive organizational development. The wild anaerobic community in the chemostat layer maintains itself through the same metabolic cycles it has maintained for 66 million years. But biological systems have vulnerabilities that self-maintenance cannot address: pathogenic disease events, invasive species introductions, toxic chemical exposure, acute habitat disruption. These vulnerabilities produce failure modes that differ from the gradual performance decline the condition-based monitoring detects in normal degradation. They produce rapid, potentially catastrophic performance loss that the biological system's own repair biology cannot address because the disruption is outside the organism's evolutionary experience. The biological infrastructure's vulnerability to these failure modes is the domain where the Terraform Operators' biological expertise is the installation's primary defense. The genetic drift monitoring program detects slow changes in the designed organism's genetic composition. The water chemistry monitoring detects gradual changes in the habitat conditions. The biological census detects gradual changes in population size and behavioral patterns. None of these are the appropriate detection system for a pathogenic disease event that kills 50% of the Ancestris vitreous colony in a week. The Terraform Operators' direct observational experience of the biological systems in their cenote is the appropriate detection system. An operator who works in proximity to the managed biological community, who makes regular observation dives in the freshwater zone, who reviews the biological census data at daily rather than weekly frequency, who notices when the Ancestris vitreous colony's behavioral patterns in a particular gallery section have changed in a way that the sensor network has not yet flagged as anomalous, can detect the onset of a disease event or an invasive species introduction before the quantitative monitoring indicators have moved outside their normal variation ranges. The Terraform Operators' sensory perception of the biological community is the biological civil engineering system's most sensitive early warning instrument. It is the detection system that the coordinating system's sensor network is the backup for, not the other way around. The sensor network can monitor more parameters more frequently and more precisely than the Terraform Operator's observational capacity. But the sensor network monitors the parameters it was specified to monitor. The Terraform Operator monitors whatever the biological community is currently doing that warrants attention, including the things no sensor was specified to measure because no founding engineer anticipated they would need to be measured. This is the Terraform Operator's irreplaceable role in the biological civil engineering system, not the routine monitoring that the sensor network performs more efficiently, but the anomaly detection that requires a biological intelligence with evolutionary experience in recognizing when something living is doing something unexpected. The coordinating system detects quantitative deviations from specified parameter ranges. The Terraform Operator detects qualitative changes in biological behavior that no parameter range captures because no parameter was specified for the behavior in question. The coordinating system manages the biological infrastructure. The Terraform Operator understands it. The combination is what makes biological civil engineering's 1,000-year design life achievable, the management efficiency of the coordinating system applied to the biological insight of the trained ecological professional, in a governance architecture that protects the biological commons from the institutional pressures that would compromise the habitat maintenance investment the ecological return requires. The Part 4 synthesis. Machines that build themselves is not literally true of any machine in the PipeDream installation. No machine produces another machine. No crystal tube section manufactures the next crystal tube section. No swarm unit fabricates the replacement swarm unit that will succeed it. The literal meaning of self-building machines does not describe anything in the cenote. The meaning that Part IV's title captures is the functional meaning. The installation's construction and maintenance capacity is self-sustaining in the sense that it does not require continuous external input to maintain its capability. The swarm units are replaced from the maintenance hub's inventory, which is replenished from the formation cenote's fabrication facility, which is supplied by the transit system's maintenance logistics. The Litho-Crustacean colony reproduces itself from the genetic architecture the founding biologists specified. The Ancestris vitreous population maintains itself through the same reproductive biology and the genetic drift monitoring program that ensures the founding specification's persistence. The mycofiltration panel's fungal network reproduces the filter medium from the substrate the installation's own waste streams provide. The construction and maintenance capacity is self-sustaining. Not self-creating, the founding installation's construction capacity was established by the founding engineers, the founding biologists, the coordinating system's initial deployment, and the core's first generation of units. But self-sustaining, once established, the capacity to expand and maintain the installation is maintained by the installation's own systems without requiring the founding generation's ongoing involvement. This self-sustaining construction and maintenance capacity is the specific property that makes the 1,000-year design life achievable without the founding generation's perpetual presence. The founding generation designed the capacity into the installation's biological and mechanical systems. The capacity maintains itself through the biological reproduction of the living components, the coordinating system's continuous operation, the Terraform Operators' ongoing certification and professional development, and the Redeemer governance framework's constitutional maintenance of the standards that all of these systems operate within. The machines that build themselves are the civilization's self-sustaining capacity to build and maintain itself, the property that distinguishes a civilization from a construction project. A construction project requires its builders to be present throughout. A civilization maintains the capacity to build itself from within itself, indefinitely, as long as the institutional infrastructure that holds the construction knowledge, manages the construction biology, and governs the construction decisions is maintained. The institutional infrastructure is Redeemer and the digital twin and the Terraform Operators and the coordinating system and the genetic archives and the master genetic archive and the biological operations manual and the construction operations manual and the master context brief that holds all of these in relationship to each other and to the formation that produced the space in which all of them operate. The machines that build themselves are not mechanical. They are civilizational. They are the systems, the knowledge, the governance, the biology, and the intelligence that allow the cenote to be inhabited continuously for 1,000 years by a civilization that maintains its own construction capacity from within its own resources. The machines that build themselves are the civilization itself. What biological civil engineering means for parts 5 through 12. The biological civil engineering systems documented in part 4 are not complete as documented here. The Litho-Crustacean's boring program is civil engineering. The food forest is also a food production system, documented in Part 8's Living Pantry Framework. The Ancestors Vitreous colony is also the visitor experience's most intimate biological encounter, documented in Part 6. The pink dolphin population is also a tourism asset, a conservation program, and a research subject, documented in Parts 5 and 8. The wild anaerobic community is also the chemostat's industrial metabolism, documented in Part 10. The biological systems do not belong to Part 4 any more than they belong to Part 5 or Part 6 or Part 10. They belong to the formation. They are the formation's biological expression, managed by the civilization's civil engineering discipline to serve functions that the formation's natural biology coincidentally performs within the ranges the civilization's infrastructure requires. The organism does not know it is civil engineering any more than the limestone knows it is being inhabited. The biological civil engineering discipline is the civilization's way of seeing, the cognitive framework through which the formation's biology becomes the infrastructure the civilization manages. Parts 5 through 12 see the same biological systems through different cognitive frameworks, as ecological communities to be understood and protected, Part 5, as experiential environments to be designed for visitors, Part 6, as safety systems to be designed against failure, Part 7, as production systems to be scaled for food security, Part 8, as governance commons to be protected from privatization, Part 9, as industrial metabolism to be managed for economic output, Part 10, as therapeutic environments to be tuned for human biology, Part 11, and as post-scarcity infrastructure to be understood as the prototype for planetary civilization, Part 12. All of these framings are true simultaneously of the same biological systems. The Ancestors Vitreous colony is civil engineering infrastructure, experiential biology, safety system maintenance, food system adjacent, governance commons, industrial metabolism support, therapeutic environment component, and post-scarcity prototype simultaneously. None of these framings exhausts the organism. None of them is more true than any other. Each is the frame the cognitive need of the moment provides. The formation holds all of the frames at once. The civilization's disciplinary frameworks, civil engineering, ecology, governance, medicine, economics, separate what the formation holds together. Part IV's disciplinary framework is civil engineering. Parts 5 through XII's disciplinary frameworks are the other ways of seeing the same biological systems the formation contains. The formation does not prefer any of the frames. The organisms perform their functions regardless of which frame the civilization uses to understand them. The limestone accepts the boring regardless of whether the civilization calls it civil engineering or geology. The food forest grows regardless of whether the civilization calls it infrastructure or ecology. The civilization's frames are its tools for managing the relationship with the formation. The formation's patience with the civilization's frames, its willingness to sustain them all simultaneously, to allow the same organism to be civil engineering and ecology and governance commons and therapeutic environment and post-scarcity prototype at once, is the formation's most fundamental civil engineering contribution. The formation is the infrastructure. The civilization is the tenant. The biological civil engineering is the relationship between them, managed carefully, governed faithfully, maintained across the generations that the 1,000-year design life requires, in the service of the civilization that the formation agreed to carry. Cross-references, Part 1, CH6, Building Without Destroying, Part 2, CH6, Designing for 1,000 Years, Part 3, CH6, The First Regional Network, Part 4, CH1, The Robot Frontier Core, Part 4, CH3, Maintenance Without Humans, Part 4, CH5, The Living Tunnel Makers, Part 5, The Engineered Ecosystem, Part 9, CH4, Redeemer's Governance OS, Part 10, CH1, The Chemostat, Part 12, CH5, Sans a priori. For Designed Organism Governance Protocol and Commons Asset Protection Procedures, see Appendix H, Governance Operations Manual. For Master Genetic Archive Maintenance Schedule and Founding Genotype Restoration Procedure, see Appendix F, Biological Operations Manual. For Mycofiltration Panel Substrate Preparation Protocol and Food Forest Seeding Methodology, see Appendix F, Biological Operations Manual. For Pre-Existing Biological Community Monitoring Indicators and Disruption Response Protocol, see Appendix A, Formation Baseline Protocol. End of Part 4, Machines That Build Themselves. Thanks for reading MXTM's newsletter. Subscribe for free to receive new posts and support my work with BTC. Or with fiat at paypal.me/MartinChartrand. Subscribe. Discussion about this episode. Comments. Res tax. Recent episodes. PipeDream Part 2. July 9th MXTM aka Pirate 1 or VJ Tsunami X. Sueño de Tuberia Part 1. July 8th MXTM aka Pirate 1 or VJ Tsunami X.
Faces, digital space, build a perfection, keeping pace. Generation, self-obsessed, chasing clicks like all the rest. Boss life, live free. Maker, bats, pain. Giants rise, code empires fall. Digital profits, claim it all. Typing manifestos in empty rooms, while servers hum ancient tunes. Prior sin, binary choice, static noise or human voice. System crash, reboot the mind, leaving old code far behind.
The criminalization of curiosity. How answers from uncanny questions became prosecutable war crimes. By Pirate First.
Pirate Firsts, the map beneath the map. Discover the truth that lies within the shadows.
Take a long look, matey. The city on the horizon be ripe for the taking, and the tide be turning in our favor as the sun dips below the waves.
La línea está dibujada. De un lado, el sueño estéril del capital. Del otro, la realidad de la supervivencia. The smart paper transitions seamlessly from the schematic view to the topographic analysis, providing immediate environmental data.
Accessing the fragmented skill data. The White Glove Protocol is now active. All systems initialize the redemption sequence. Keep going, you are doing great.
The cage is unlocked, but we choose the bars. Renting our lives, forgetting the source. We are the sovereign authors of this digital verse. Reclaim the dowry, break the curse.
In the post-scarcity era, rarity is you. When everything is free, your genome is the only asset that remains.
Structure layers are now operational across the Tulum Sustainable Development Zone. Despite minor data corruption errors regarding land narrative, the impact report remains positive.
The simulation data confirms critical interference levels across the territory. Narrative load is unstable.
Be advised, paranoia is now a product. The risk assessment is maximum.
Remain sovereign amid the noise. As the interference level spikes, their simulation engagement increases.
We must decipher the reality of this update.
Attention.
Signal integrity is failing.
We have 4% uptime before the broadcast load collapses. Decipher the transmission and act immediately.
4-2.
The one a post-scarcity transition doctrine. A post-scarcity secession doctrine.
El desplazamiento reduce la latencia y el aprendizaje se vuelve coherente. El sistema abandona